Night falls on a world lit only by starlight. In the deep silence, ancient people lift their eyes to the sky. Above them arches a dazzling river of stars, the Milky Way, unmarred by any earthly light. Without city lights or haze, the night sky is a breathtaking dome of bright points on dark velvet. The fire's embers glow faintly, but overhead the cosmos shines in full glory. They see patterns among the stars, familiar yet mysterious. In this tranquil darkness, the first astronomers are not scientists with telescopes, but humble observers, our distant ancestors filled with wonder. For countless generations, the night sky is humanity's companion and guide. By observing the heavens, early people learn the rhythm of nature. They watch the sun rise in the east and set in the west, bringing day and night in a reliable cycle. They mark the gentle waxing and waning of the moon, counting out the months by its changing face. They notice certain stars creeping across the sky with the seasons, new constellations heralding planting time, others signaling the oncoming winter. Bit by bit, patterns emerge from the cosmic tapestry, teaching them when to seek game, when to harvest, when to brace for the cold. Under ancient skies, those first observers begin not only to survive by the stars, but to dream under them. What are these celestial lights? Campfire stories grow around them. Perhaps the bright band of the Milky Way is the spirit of a great river in the sky. Maybe the sudden streak of a meteor is a divine spark from a celestial forge. Each shooting star, each eclipse of the moon, stirs both awe and curiosity. In darkness, our ancestors find a canvas for their fears and hopes, painting it with imagination and myth. But beyond wonder, there is need. The sky is also a calendar and a compass. Knowing when rains will return, or when cold will come, could mean life or death for early communities. So they study the sky with purpose as well as reverence. They begin to track time by the heavens, observing that the moon goes through her phases in a regular cycle, and that the sun's rising point along the horizon shifts a little each day through the year and then back again. The heavens offer a kind of order amid the uncertainty of earthly life, if one pays close attention. Imagine a small family clan, tens of thousands of years ago, huddled around a crackling fire. One of them picks up an animal bone and scratches a notch for each day the moon has appeared since it was new. Night after night, they add marks. They notice it takes about 30 marks, roughly 30 days, for the moon to return to the same thin crescent shape. Without knowing the number, they've discovered the length of a month. In these simple scratchings, we see the dawn of a calendar, an attempt to capture time by the glow of the moon. Archaeologists have indeed found ancient bones and sticks with sequences of notches, as if someone long ago was counting days or moon phases. These are hints of humanity's first attempts to record the sky's cycle. Even without writing or numbers, people had begun to observe and remember the patterns above. They carried this knowledge in stories and in memory, teaching each new generation when the rains would come, or when herds would migrate, all by the signs in the sky. Over time, early observers sought more permanent ways to mark the heavens' progress. Great effort went into shaping the very landscape into cosmic calendars. In a valley in what is now Scotland, around 10,000 years ago, people dug a series of pits in the earth. These pits seem to align with the sunrise of midwinter's shortest day. Archaeologists believe this could be the world's oldest known calendar. 12 pits for 12 lunar cycles, calibrated so that when the solstice sun rose in line, the cycle would restart. One can picture those ancient people watching the horizon on a cold dawn, waiting for the sun to rise over their marker and tell them the new year had begun. As human societies grew more organized, their efforts to track the sky became bolder and more permanent. Across Europe and beyond, people raised stones and built circular monuments aligned to the sun's path. One example lies on a broad plain in what is now Germany. A wide circle of earth and wooden posts erected about 7,000 years ago. It had gates, or openings, that faced the points on the horizon where the sun rises and sets on the solstices. On the longest day and the shortest day, sunlight would stream through those openings, signalling those critical turning points of the year. These early henges were observatories without roofs, merging architecture with astronomy. A testament to Bronze Age skywatching was unearthed not long ago in Germany, the Nebra Sky Disk. This extraordinary artifact, dating to around 1600 BC, is a bronze disk about the size of a large plate, patinated green with age and inlaid with gold symbols. Cleaned and studied, the disk revealed golden shapes arranged on its surface. A large round gold circle that appears to be the sun, or perhaps a full moon, a smaller gold crescent, and a cluster of 7 tiny gold dots representing the Pleiades star cluster. 2 golden arcs along the rim span about 82 degrees each, the angle between the sun's setting point at summer solstice and winter solstice at that latitude. The Nebra Sky Disk is the oldest concrete depiction of the cosmos yet found. It suggests that people 3,600 years ago had a sophisticated grasp of celestial patterns. Scholars believe the disk was used as a kind of astronomical guide. By aligning its edge arcs with the solstice sunset points on the horizon, one could calibrate a lunisolar calendar. In other words, the disk might have helped its owners decide when to insert an extra lunar month to keep their calendar in sync with the solar year. This incredible object, buried for millennia and only recently discovered, testifies that long before written records, humans were not only observing the heavens, but creating tools to track the sky's order. Even earlier, in the desolate Sahara Desert of Africa, people erected stones to read the sky. At a place called Nabta Playa, roughly 7,000 years ago, a stone circle was laid out on the open desert floor. Its stones seem to have been aligned to the rising of the sun at the summer solstice, the longest day. For the cattle-herding people of that region, this would have been a vital sign. The solstice indicated the season when life-giving rains were due. Imagine them gathering at dawn, watching the first rays of the midsummer sun line up with their standing stones, a celestial signal that water and abundance would soon return to the parched land. Some researchers believe the stones of Nabta Playa might also correspond to bright stars. 3 stones in the circle may mirror the 3 stars of Orion's belt, and other alignments may point towards Sirius and other important stars. If true, it means these ancient skywatchers not only followed the sun, but also mapped certain stars. They created a kind of observatory in the sand, one that bridged earth and sky in a sacred space. On the far side of Europe, other monuments rose to catch the light of heaven. In Ireland, over 5,000 years ago, people built a great mound tomb at Newgrange, designed with cosmic intent. Within this massive earth mound, they constructed a long, narrow passage lined with stone slabs etched in spirals and mysterious symbols. These carvings may themselves have held astronomical meaning or ritual significance. For most of the year, the inner chamber at the end of the passage lay in cold, silent darkness. But at the winter solstice, at dawn, something extraordinary happened. A small opening above the entrance allowed a shaft of sunlight to penetrate the mound. On the shortest day of the year, the rising sun's rays would travel all the way down the passage and illuminate the inner chamber for a few brief minutes. It was as if the sun itself entered the heart of the earth, rekindling light at the darkest time. This precise alignment required astonishing care in construction. Those ancient builders knew exactly when and where the sun would shine. They built a monument that would come alive with light on that one crucial morning each year. On the Salisbury Plain of England, one of the most famous ancient observatories took shape: Stonehenge. Massive stones were dragged and erected in rings and horseshoe patterns, starting around 5,000 years ago. The final arrangement, still standing today, was completed a bit later, with towering sarsen blocks capped by lintels to form great stone arches. Stonehenge is aligned to the movements of the sun. At dawn, on the summer solstice, a person standing at the center of the stone circle will see the sun rising precisely over a designated outlying marker, known as the heel stone. Then, at the winter solstice, on the year's shortest day, the sun sets in alignment between the largest uprights of Stonehenge, as if sinking in a giant stone doorway. These alignments were no accident. Generations of observers studied the sun's path and arranged the monument's layout accordingly, using the heavens as their guide. We can imagine the ancient families of that land gathering at Stonehenge on those sacred dawns and dusks. Wrapped in furs against the chill, they watch in reverence as the great stone circle and the sky work together to mark the turning of the year. Fires might have been lit around the ring of stones, illuminating them from below as the sun's first or last rays touched the horizon. It must have been a moment of communal awe and reassurance, a promise that the cycle of seasons, of light and dark, would continue anew, as it always had. Across the ocean, in the Americas, ancient peoples also built structures aligned with the sky. In a desert valley of Peru, the city of Caral flourished around the same time as the Egyptian pyramids. There, 6 pyramidal structures and other monuments were carefully oriented. Evidence suggests they were aligned to the sun's movements. For instance, certain buildings at Caral face the exact point on the horizon where the sun sets on a particular day of the year. These alignments likely helped its people track seasons for agriculture. Though separated by oceans, the people of Caral, like those of Stonehenge or Nabta Playa, found their own way to connect heaven and earth in their city planning. Later in Peru, by about 300 BC, an intriguing complex called Chanquillo was built as a dedicated solar observatory. It consisted of a line of 13 stone towers on a low ridge running north-south. By looking from specific observation points, ancient sky watchers could see the sun rise or set each day between different pairs of these towers. Over the year, the sunrise and sunset positions migrated along the row of towers. At the solstices, the sun would appear at the end of the line of towers, and at the equinoxes, near the center. Thus, Chanquillo provided a complete solar calendar in stone. Although Chanquillo comes toward the end of our dawn period, it reflects the same desire present throughout prehistory: to pin down the sky's schedule and make the year predictable. All these ancient structures and alignments reveal something profound. Early humans had begun to observe regular cycles in the sky and tie their lives to them. Across different continents, without ever communicating with each other, our ancestors converged on the idea that the sky's rhythms could guide human life. Yet the practical tracking of time was only one facet of humanity's relationship with the cosmos. The other was spiritual and imaginative. As people gazed up at the glittering night, they didn't see mere objects. They saw actors in a grand cosmic drama. Each culture wove its own tapestry of myth across the stars, finding gods, heroes, animals, and cosmic meanings in the patterns above. In ancient Mesopotamia, where some of the first great cities arose, people believed the sky was alive with divine powers. The Sumerians and Babylonians looked up and saw their gods among the stars and wandering planets. The moon was a god named Nana, later called Sin, who journeyed across the sky each month, disappearing at the dark of the moon and returning reborn as a crescent. The brilliant planet Venus was Inanna, later known as Ishtar, the goddess of love and war. She appeared alternately as the morning star and the evening star. When Venus vanished for several days in transition between those appearances, they imagined it as the goddess descending into the underworld and then returning to the sky. The great planet Jupiter, slow-moving among the stars, was associated with Marduk, chief deity of Babylon. Mars, red and ominous, was linked to Nergal, the god of war and plague. To the Mesopotamian stargazers, the movements of these wandering stars, planets, were messages from the gods. Mesopotamian myths taught that the very world itself was shaped by cosmic forces. In their creation story, the universe began in chaos, a swirling primeval sea. The goddess Tiamat, a dragon of the salt waters, rose up against the younger gods, threatening cosmic order. Marduk, the hero god of Babylon, challenged her. After a titanic battle, he split Tiamat's body in two. From one half he fashioned the sky, from the other half the earth. Thus, in their view, the heavens were literally formed from the body of a slain dragon, stretched out as a domed firmament over the world. They imagined the earth as a flat disk floating on a vast cosmic ocean, and the sky as a solid vault above, holding back waters of heaven. The stars and planets moved across this vault, along paths set by divine decree. When rare phenomena occurred, say a comet with its tail streaming, or an eclipse that turned day to dusk, it meant the normal order was disturbed. Such events were interpreted as warnings from the gods, perhaps a sign of divine displeasure, or a harbinger of great change for the kingdom. For the people of Mesopotamia, reading the sky was a way to stay attuned to the will of the heavens. Under the clear skies of ancient Egypt, a different cosmic story unfolded. The Egyptians personified the heavens as a goddess named Nut. They imagined her as a great mother arching over the earth, her body dark blue and covered in stars. At the eastern horizon, each dawn, Nut would give birth to the sun, the god Ra, who then sailed across the sky in his bright boat. At sunset in the west, Nut would swallow the sun, and Ra would travel through the underworld during the night, only to be reborn by morning. This daily cycle of sunrise and sunset, death and rebirth, was at the heart of Egyptian belief, symbolizing the promise of renewal and the triumph of order over darkness. The night sky was also full of meaning for the Egyptians. They watched the stars that never set, those that circle around the North Pole each night without dipping below the horizon. These they called the imperishable or unwearying stars, and they imagined them as a realm of eternity. Pharaohs, in particular, hoped to join those deathless stars after they departed this world. The pyramids they built were not only monumental tombs, but also symbolic launch pads to the heavens. Indeed, the Great Pyramid of Giza is oriented almost perfectly to the cardinal directions, especially toward true north. Inside its massive structure, narrow shafts were engineered to point towards specific stars in the northern and southern skies. One shaft aimed at the region of the sky containing those imperishable circumpolar stars, and another toward the prominent constellation of Orion. In later pyramids and tombs, Egyptians even painted star charts on ceilings, reflections of their effort to bring the heavens into their architecture and art. To the Egyptians, aligning their sacred spaces with the cosmos was essential. It ensured that their ceremonies and the pharaoh's soul were in harmony with the divine order of the sky. Picture an Egyptian dawn over 4,000 years ago. On the flat rooftop of a temple by the Nile, a priest stands facing the eastern horizon. The stars are fading as the sky grows lighter. He holds a small water clock, watching the drip of water to measure time, and he waits in silence for a sign. In the stillness, he whispers a prayer to the goddess Isis, guardian of the star he seeks. Then, just before the sun's glow, a single blue-white star flashes into view low in the east. Sopdet, the sacred star we call Sirius. It is the first time in many months that Sirius has risen in the pre-dawn sky. The priest catches his breath and lifts his arms in reverence. This heliacal rising of Sirius is what he has awaited. It heralds the imminent flooding of the Nile. He will rush to tell the pharaoh and the people that the new year has begun. In that moment, careful observation and spiritual significance become one. The stars have guided them, promising that life-giving waters will soon return on cue. In ancient India, the skies were woven into rich mythologies and philosophical inquiries. Early Hindu thought imagined the cosmos in grand cycles. One famous hymn from the Rig Veda muses about the creation of the universe by declaring, "There was neither existence nor non-existence then. Who really knows how it all came to be?" This reflective approach shows that the night sky provoked deep questions even in antiquity. Yet Indian tradition also provided vivid celestial imagery. They spoke of a cosmic egg, the Brahmanda, from which the universe hatched at the beginning of time. They told of the god Brahma creating and recreating the universe in vast eons called kalpas, each lasting billions of years. Time, in the Indian cosmic vision, was cyclical and immense, like the constant turning of the heavens. Indian star lore is filled with characters and symbols. The 7 bright stars of the Big Dipper were seen as the Saptarishi, 7 great sages of antiquity immortalized in the sky. Each night, they wheel around the pole star, Dhruva, which holds a special, fixed place at the center of the sky. There is a beloved legend of Dhruva, a young boy whose unwavering devotion earned him a boon from the gods. He was transformed into the pole star itself, to shine forever as a guide. Indeed, Dhruva remains the Sanskrit name for the North Star, the steadfast beacon around which the heavens turn. To this day, traditional stories in India recount how Dhruva's dedication placed him in the heavens as an eternal light. Ancient Indians also divided the sky into 27 or 28 sections along the moon's path, known as nakshatras. Each nakshatra was associated with a particular star or star cluster, and often linked to a deity or story. For example, the Pleiades cluster was called Kritika and personified as a group of nurturing mothers. In one tale, they are the foster mothers of the war god Kartikeya. The appearance of certain nakshatras at dusk or dawn would signal the proper time to perform seasonal rituals or plant crops. In this way, Indian society tied its calendar to the stars, blending practical timekeeping with mythic significance. They also paid close attention to the 5 visible planets, known as grahas. The correlations between planets and gods were drawn. For instance, Jupiter was called Brihaspati, and seen as a divine teacher. Venus was Shukra, associated with beauty and passion. Astrology, Jyotisha, became a key part of their culture, using planetary motions to guide decisions and foresee auspicious times. Yet behind these astrological readings lay careful, nightly observation. Only by patiently watching when each star or planet rose and set could they maintain an accurate calendar and know when to add extra months or perform sacred rites. Thus, mythology and observation worked hand in hand in ancient India. Far to the east, in ancient China, people also wove the cosmos into their worldview. They pictured the sky as a great dome or sphere rotating above a flat earth, not entirely unlike the Mesopotamian idea. But Chinese cosmology emphasized harmony between heaven and earth. At the very top of the sky lay the North Star, which they regarded as the celestial emperor's throne. They called the area around it the purple forbidden enclosure, essentially the heavenly palace. Just as all subjects revolved around the emperor on earth, so too did the stars circle the pole in heaven around an imperial center. The Chinese grouped stars into constellations that often reflected their own society and legends. Instead of the familiar Greek constellations, they had their own system. The sky was divided into regions symbolized by 4 mythic creatures: the azure dragon of the east, the white tiger of the west, the black tortoise of the north, and the vermilion bird of the south. Within these quadrants, they designated 28 lunar lodges or mansions, XRU, through which the moon passed, akin to the Indian nakshatras. Each mansion had a name and significance, often tied to images of animals, markets, chariots, or other aspects of life. By tracking the moon's progress through these mansions, they organized their calendar and rituals with great care. Like other cultures, the Chinese interpreted unusual celestial events as omens. For instance, they believed a solar or lunar eclipse occurred when a great dragon was attempting to devour the sun or moon. People would create noise and commotion, beating drums, gongs, and even shooting arrows into the sky to scare the dragon away and save the heavenly bodies. Such traditions persisted for millennia, reflecting the mix of fear and reverence these events inspired. In the imperial court of ancient China, the stakes of astronomy could be life and death. A legend tells of a day around 2237 BC when the midday sky suddenly went dark in a solar eclipse that court astronomers failed to predict. Panic swept through the capital. People clanged on drums and gongs to frighten the devouring dragon, and chaos reigned. Emperor Zhongkang was furious with his chief star watchers, 2 astronomers named Shi and Ho, who were absent instead of issuing a warning. For this lapse, they were executed. Whether or not this tale is fully true, it shows how seriously the Chinese valued foreknowledge of the heavens. Now imagine a later era, centuries after that fateful eclipse. Chinese astronomers have refined their methods and can often anticipate eclipses. When they calculate that the sun will darken on a certain day, the court prepares. At the appointed hour, daylight turns eerie and dim as the moon's shadow bites into the sun, just as foretold. This time, no panic erupts. People still drum and clamour as tradition dictates, but they do so calmly, confident the light will return. The emperor watches, trusting the astronomers who aligned human expectations with heaven's timing. When sunlight returns, it reaffirms not only that the celestial dragon has been vanquished, but that knowledge and foresight have prevailed. The ability to predict the sky's behavior has strengthened the harmony between heaven and earth. The Chinese also regarded comets, with their glowing tails, as ominous broom stars. A comet's sudden appearance was likened to a celestial broom sweeping away the old order, often interpreted as a sign that a dynasty's time was ending, or that turmoil lay ahead. Ancient Chinese chronicles meticulously noted each comet and nova. Whenever a guest star, what we now recognize as a nova or supernova, or comet appeared, imperial astronomers scoured their archives and advised the emperor on its meaning. To them, the heavens were a communication channel between the cosmos and the state. If misrule or chaos threatened the land, the skies would send warnings. If harmony prevailed, the heavens would remain in their regular course. Thus, watching the sky was part of governance itself in China, and astronomy was both a scientific endeavor and a safeguard of the realm's divine mandate. Meanwhile, around the Mediterranean, the ancient Greeks were mapping the sky with their own stories. They inherited some constellation patterns from Mesopotamia and Egypt, but breathed new life into them through Greek mythology. To the Greeks, the night was a vast stage for the tales of gods and heroes. One swath of stars became Andromeda, a princess chained to a rock as a sacrifice to a sea monster, and nearby shone Perseus, the hero who rescued her, brandishing the head of Medusa, marked by the blinking star Algol. Not far away was Cetus, the sea monster itself, commemorated in the stars. Every arrangement of stars became an episode of legend. They imagined Orion as a giant hunter striding across the sky. In their stories, Orion once boasted he would hunt every animal on earth, and as a lesson in humility, the gods placed him among the stars. There he appears to chase eternally after the Pleiades, 7 sister stars who flee his advance. The Big Dipper formed part of Ursa Major, the Great Bear, which the gods set in the heavens to commemorate Callisto, a maiden turned into a bear by Zeus. Even the Milky Band of the galaxy had its legend. Some Greeks said it was a spray of milk from the breast of the goddess Hera, spilled across the sky. Thus, the Greeks, like others, filled the darkness with familiar figures, turning the night into a storybook of their culture's triumphs and tragedies. Indeed, nearly every culture around the world found its own stories in the stars. Across North America, many indigenous peoples also saw a great bear in the night sky. For some, the 4 stars of what we call the Big Dipper's bowl formed a mighty bear, and the 3 stars of the handle were hunters chasing it. One legend says that each autumn the hunters finally catch the bear and slay it, and its spilled blood turns the leaves of the trees red. By spring, the bear's spirit returns to life, and the cosmic chase begins anew. This was a way of explaining the cycle of seasons through the drama of the sky. In the Southern Hemisphere, Australian Aboriginal peoples looked to the Milky Way not for patterns of stars, but for shapes of darkness. They saw a great emu outlined by dark nebulae, the emu in the sky, stretching across the starry band. When this celestial emu appears in a certain posture at dusk, it signals that it's time to gather emu eggs on Earth. Thus, a mythic creature in the sky served as a seasonal calendar. The Maori of New Zealand, meanwhile, watched for the winter rising of the Pleiades, which they call Matariki, just before dawn. Its return each year marked the New Year festival, a time of remembrance and renewal as the darkest days of winter passed. Out on the vast Pacific Ocean, Polynesian navigators used the stars in an even more direct way. They memorized intricate star compasses, patterns of stars that rose and set along specific bearings, and encoded this knowledge in stories, chants, and mental maps. By knowing exactly which star rose at a given point on the horizon, they could hold course toward distant islands over the open sea. For them, the night sky was a living map. Each star had a role in guiding voyagers across an otherwise trackless expanse. From the Arctic to the equator to the far south, humans used the sky's stories not just to entertain or explain, but to live, to know when to plant, when to harvest, when to set sail, and when to celebrate. The cosmos became a mirror of the world's patterns and a compass for journeys. Ancient astronomy was often intertwined with a society's concept of cosmic order. For the Egyptians, the regularity of the stars and seasons was an expression of Ma'at, the divine order and justice that the gods established, and the pharaoh was duty-bound to uphold. To maintain Ma'at, Egyptian priests kept the calendar aligned with celestial cycles and timed rituals to cosmic events, believing that doing so helped sustain harmony in their land. In Vedic India, a similar concept called urta described the cosmic order. Performing sacrifices at the correct astrological times and keeping time by the skies were ways to uphold urta on earth. In ancient China, the harmony between heaven and earth was paramount. It was said that an emperor's virtue, or lack thereof, would be mirrored by signs in the sky. If he ruled justly and the realm was in balance, the heavens would remain auspicious. If not, comets, eclipses, and strange apparitions might appear as heavenly warnings. This idea became known as the mandate of heaven. Thus, observing the heavens was not just a scientific pursuit, but also a moral duty. By following the sky's rhythms, ancient peoples felt they were aligning human life with the fundamental order of the cosmos. Astronomy in these cultures carried profound significance. It was part of keeping the world itself in balance. From all these stories and beliefs, a new idea slowly emerged. The heavens were not just the capricious realm of gods, but followed patterns that humans could understand and even predict. Ancient astronomers still spoke of omens and divinities, but with each careful observation, they uncovered more regularity. The desire to know what would happen next in the sky led to the birth of organized astronomy, the moment when sky watching became a true science. In temples and royal courts, priestly observers moved beyond mere sign reading. They began systematically charting the heavens. They kept records, compared notes across generations, and even dared to predict celestial events. It was a new dawn. The cosmos seen not only as the theatre of gods, but as a great clockwork that human minds could learn to read. Even ordinary people used the stars as guides in day-to-day life. The Greek poet Hesiod, writing around the 8th century BC, advised farmers when to sow and harvest by watching the seasonal stars. In his Works and Days, he notes that when the Pleiades star cluster rises just before dawn, it is time to harvest, and when it sets at dusk, it is time to plough the fields. Such practical lore shows how myth and observation merged in daily life. The Pleiades were not only the seven sisters of legend, but also a celestial calendar in the sky. Greek sailors likewise navigated by the stars, following the rising of Arcturus, or steering by the fixed North Star. In these ways, knowledge of the heavens guided everyday activities, even as scientific theories of the cosmos slowly took shape. In Mesopotamia, this shift from seeing omens to finding order was dramatic and influential. For ages, Babylonian priests observed the sky to advise their kings, keeping watch each night from the tops of tall ziggurats, stepped temple towers. They filled clay tablets with meticulous records: when eclipses occurred, where planets rose, how the stars twinkled. By around 1000 BC, these accumulated observations began to reveal patterns. Imagine a warm night in ancient Babylon. Atop a tall ziggurat temple, a robed priest astronomer stands under a glittering canopy of stars. He holds a damp clay tablet in one hand and a stylus in the other. By the flicker of an oil lamp, he etches cuneiform symbols onto the clay, recording the night sky. He notes the time a certain star rises, the exact moment the moon touches the horizon, the position of bright Jupiter relative to nearby stars. Such a scene played out night after night, year after year. Each observation by itself was small, but together, over generations, these records grew into a vast treasury of knowledge. Unknown to that lone watcher, the accumulated tablets would one day reveal that eclipses and planetary motions followed repeatable cycles. There in the silent night, he is not only serving the gods by watching for omens, he is also, step by step, unlocking patterns in the sky's flow of time. The sky watchers noticed, for example, that lunar eclipses often recurred in a regular rhythm. If a blood-red lunar eclipse happened one year, a similar one would happen again after a fixed interval of years and months. We now know this as the Saros cycle, about 18 years long. The Babylonians, through patient record-keeping, discovered it. Even if they did not understand the geometry of sun, earth, and moon that causes eclipses, they realized they could predict roughly when the next eclipse would occur. A terrifying omen could thus be anticipated and prepared for, a profound shift from passive fear to proactive knowledge. Beyond eclipses, Babylonian astronomers turned their attention to the wandering stars, the planets, and started tracking them with new rigor. They carefully timed the cycles of Venus, for example. One surviving text, the Venus tablet of King Amisaduqa, lists the dates when Venus first appears as a morning star or evening star over many years. From such data, they learned that Venus's appearances repeat on a cycle of about 584 days. They similarly tracked the movements of Jupiter, Mars, Mercury, and Saturn, observing how these planets sometimes slowed, stopped, and even moved backward, retrograde, against the starry background, and noting the intervals of these behaviors. To bring order to their observations, the Babylonians invented a kind of celestial coordinate system. They divided the band of sky through which the sun, moon, and planets travel, the ecliptic, into sections. Over time, they formalized the concept of the zodiac. 12 equal segments, each containing a constellation, the bull, the lion, the scorpion, and so on. Each sign covered 1/12 of the full circle of the sky, 30 degrees out of 360. This division into 360 degrees meshed well with their base 60 mathematics. With this system, they could pinpoint where a planet was and would be. Instead of saying, Mars is in the constellation of the bull, they could record, Mars is 10 degrees into Taurus, giving a quantitative measure. This precision made it possible to create tables predicting where a planet would be months or years in the future. By the 4th century BC, Babylonian astronomy had become highly technical, even employing some early arithmetic algorithms to compute motions. What began as sky watching for omens had evolved into a science of celestial cycles. Their methods and records would later spread beyond Mesopotamia, informing astronomical traditions in Greece, India, and beyond. Only fragments of Babylonian celestial lore have survived. Many clay tablets have crumbled. But those that remain show how advanced it became. The systematic records allowed for the observation of repeating cycles, and Babylonian scholars developed a new empirical approach. They no longer solely relied on divine signs. They employed internal logic and patterns within their planetary models. This approach to astronomy was adopted and further developed in the Greek world and beyond. Indeed, nearly all subsequent branches of astronomy, in Hellenistic Egypt, in India, in the Islamic world, and in medieval Europe, built upon the foundations laid by those Babylonian skywatchers. In ancient China, astronomy became a refined state-supported science, driven by the needs of calendar making and governance. By the Zhou dynasty, around 1256 BC, the court astronomers were responsible for maintaining a precise calendar. The Chinese calendar was lunisolar. It counted months by the moon, but adjusted to the sun's yearly cycle. This meant that every few years, an extra month had to be inserted to keep the seasons aligned, a process called intercalation. Deciding when to add that leap month required careful observation of the skies. Chinese astronomers employed instruments and techniques to make these observations. One of the simplest was the gnomon, a straight pole or pillar set upright in the ground. By measuring the length of its noontime shadow each day, they could track the sun's changing height in the sky. At the winter solstice, the noon shadow is longest. At summer solstice, it's shortest. By noting these extremes, they gauged the solar year's length quite accurately. They also observed the risings of certain bright stars at dawn or dusk. For example, when the red star Antares first rose in the east at dawn, after a period of invisibility, it signaled the arrival of summer. Such heliacal star risings served as seasonal markers, anchoring the agricultural calendar. This drive for accuracy led the Chinese to create detailed star catalogues. As early as the 4th century BC, astronomers like Shi Shen and Gan De compiled lists of hundreds of stars and their positions. They identified stars within the lunar mansions and other constellations, effectively mapping the sky as they knew it. By the Han Dynasty, around the 2nd century BC, imperial scholars like Zhang Heng were building sophisticated devices to model the heavens. They crafted armillary spheres, bronze models of the sky with rings representing the equator and ecliptic, to measure the coordinates of celestial bodies. All these efforts served a purpose: to refine the calendar, to predict astronomical events, and to ensure that heaven and earth remained in harmony. Chinese astronomers gradually learned techniques to predict eclipses as well. They observed how lunar eclipses followed a pattern and created algorithms to forecast when one might occur. By the 1st century AD, records show they could often anticipate eclipses and record them accurately. This was a far cry from the earlier days when an eclipse could catch the court by surprise. Through diligence, the sky became a bit less capricious and more quantifiable in China. Even so, astronomy remained tied to statecraft, a means to uphold the mandate of heaven by demonstrating that the emperor understood the cosmic order. In India, the systematic study of the sky was eventually codified in a treatise known as the Vedanga Jyotisha. Compiled perhaps toward the end of the 1st millennium BC, drawing on much older observations, this concise text provided rules for calculating the timing of new and full moons and for inserting leap months. It shows that Indian priests required precise calendars for scheduling sacred rituals, so astronomy, Jyotisha, became an essential scholarly discipline. They divided the year into 6 seasons and recognized 27 or 28 nakshatras, the lunar mansions, marking the moon's progress through the zodiac. By around 500 BC, Indian astronomers were using a 360-degree circle, an idea likely influenced by Mesopotamia, and developing geometric methods to describe the motions of the sun and moon. They divided the day into measured units using devices like water clocks and sundials. Their star law identified the pole star, Dhruva, as the fixed pivot of the sky, and they tracked the 5 visible planets with great care. Though much of this knowledge was intertwined with astrology and myth, the technical skill involved in aligning lunar months with the solar year shows a strong empirical tradition. In later centuries, Indian astronomy would blossom further, especially after absorbing Greek influences, but already in this early era, its foundations were being laid through systematic observation and calculation. Meanwhile, across the ocean in the Americas, organized sky watching also reached remarkable heights. The Maya civilization, in what is now Mexico and Central America, developed intricate calendars closely tied to astronomical observations. By the first millennium AD, many centuries after the earlier Old World developments we've been discussing, Maya astronomer priests had refined the measurement of the solar year, the synodic cycle of Venus, and even eclipse cycles with striking accuracy. Their cities had dedicated observatories, and their most important rituals were timed to celestial events. Dusk falls long ago over a Maya city in Central America. Atop a pyramid known today as El Caracol, a circular stone observatory, a priest astronomer stands gazing at the western sky. The humid air is alive with the sounds of jungle creatures settling as the light fades. Stars begin to appear one by one. He pays them little mind, focusing instead on one particularly bright object that soon emerges low in the twilight. It is Venus, the evening star. The priest nods to himself and notes the position and timing on a codex chart. This evening's appearance of Venus is right on schedule according to the cycles his forebears have recorded. The Maya observed Venus with astonishing precision, timing its first and last visibilities to guide their affairs. Some wars and major ceremonies were planned based on its cycle. Tonight, the evening star confirms that the calendar is in harmony with the heavens. In a few hours, Venus will sink below the horizon. The astronomer priest will descend the pyramid and report to the lords that all is as expected in the cosmos. His vigilant watch has ensured that the plans of the city remain in step with the grand clockwork of the sky. The Mediterranean world, too, saw the transition from mythic interpretation to measurement and prediction. By the 6th century BC, Greek scholars, benefiting from Babylonian and Egyptian knowledge, were beginning to ask more scientific questions about the sky. A famous example is the philosopher Thales of Miletus, who reportedly predicted a solar eclipse in 585 BC, astonishing his contemporaries. Whether he did so by savvy use of Babylonian eclipse cycles or simple luck, it showed a new confidence that nature's events followed patterns that could be anticipated. Around the same time, Pythagoras and his students realized that the morning star and evening star, the two personas of Venus at dawn and dusk, were one and the same object. This important insight united two celestial phenomena under one explanation. Greek thinkers soon ventured bold hypotheses about the structure of the cosmos. By the 5th and 4th centuries BC, philosophers like Aristotle argued that Earth was not flat, but a sphere, pointing to the curved shadow it casts on the moon during lunar eclipses as evidence. They correctly understood that the moon's light is reflected sunlight, and that lunar eclipses occur when Earth comes directly between the sun and moon. Some Greek astronomers even proposed revolutionary ideas. Aristarchus of Samos, in the 3rd century BC, suggested the radical notion that Earth might orbit the sun, a heliocentric theory. Although this idea didn't gain traction at the time. In the 3rd century BC, a Greek scholar in Egypt performed a brilliant experiment under the midday sun. His name was Eratosthenes, and he was the chief librarian of the Great Library of Alexandria. He had heard that at noon on the summer solstice in the city of Syena, far to the south, near today's Aswan, the sun shone straight down into wells and vertical poles cast no shadow. On the same date and time in Alexandria, Eratosthenes placed a gnomon, a vertical rod, and measured its shadow. he found the sun was not directly overhead there. The rod did cast a shadow, meaning the sun's rays hit the ground at an angle. He measured the angle of the shadow to be about 7.2 degrees. Eratosthenes realized that if Earth were flat, the sun's angle at noon would be the same everywhere. The differing angles implied Earth's surface was curved. Furthermore, 7.2 degrees is roughly 1/50th of a full circle, 360 degrees. He deduced that the distance from Alexandria to Cyane, about 5,000 stadia, was about 1/50th of Earth's circumference. Multiplying that distance by 50, he arrived at a figure for Earth's girth. In modern units, his result was on the order of 40,000 kilometers, astonishingly close to the actual value. With simple observations and geometry, Eratosthenes had not only affirmed that Earth is round, an idea already suspected by some, but measured its size. It was one of the crowning achievements of ancient astronomy, showing how far methods had come from the days of sky-gazing purely for omens. By the end of the ancient period, the accumulated knowledge of Babylonians, Egyptians, Chinese, Indians, Greeks, and others had firmly established astronomy as a true discipline. The motions of heavenly bodies could be measured, catalogued, and even predicted with reasonable accuracy. The sky was no longer utterly inscrutable. It was a vast system governed by principles that human minds were beginning to grasp. What began as humble sky-watching had evolved into a genuine science of the stars, setting the stage for further breakthroughs in the millennia to come. Throughout antiquity, astronomy was deeply intertwined with astrology. The ancients did not separate observing the sky from the belief that it influenced human destinies. In Babylonia, detailed celestial observations always came with interpretations. If Jupiter shone especially bright, it was a fortunate omen for the king. If an eclipse occurred, it portended danger unless rituals were performed to appease the heavens. As their observational techniques improved, predictive astrology grew more elaborate too. By the 5th century BC, Babylonian and Egyptian scholars had developed the concept of the horoscope, the idea that the positions of the sun, moon, and planets at the moment of someone's birth could shape their personality and fate. The practice spread and gained sophistication. The Greeks of the Hellenistic era embraced horoscopic astrology, blending it with their philosophical notions of cosmic harmony. Even the renowned astronomer Ptolemy, in the 2nd century AD, wrote about astrology alongside his work on planetary motions. Thus, ancient astronomy, while laying the groundwork for a scientific approach to the heavens, remained intertwined with the search for divine meaning. The night sky was not only a vast clockwork, but also a mirror believed to reflect events on Earth. This dual legacy, astronomy as both measurement and divination, would persist for many centuries. As we come to the end of this journey through the dawn of astronomy, we see humanity slowly awakening to the cosmos. In the beginning, our ancestors huddled in darkness, spinning tales about sky gods and monsters, terrified by eclipses, enchanted by the Milky Way. But over millennia, they learned to recognize patterns and to trust that the sky's phenomena were not random. From fearing an eclipse as a dragon's attack, they progressed to predicting its return through patient observation. From merely telling stories about the morning star, they learned to chart Venus's cycle across the years. This was the first light of understanding, a delicate dawn after a long night of wonder. Yet even as they brought the heavens into focus, those ancient astronomers never lost their awe. They could align massive monuments with celestial precision, but they also offered prayers and songs to the sky. They inscribed calculations on clay tablets and papyrus, all the while mindful that these numbers described the movements of divine lights above. In their midnight vigils, on a Babylonian ziggurat, an Egyptian temple roof, a Chinese tower. They felt the mystery of the universe as a profound presence. They were scientists and priests at once, blending careful measurement with reverence. We still mark time by the sky. Our modern months and years descend from those first careful reckonings of the sun and moon. We still find our way by heavenly cues. Even today, navigators and spacecraft use star positions for guidance, heirs to the practice of steering by the stars. Our constellations preserve the heritage of Sumer, Egypt, Greece, and other early cultures. The story of astronomy is a human story, a continuous thread weaving the hopes of people thousands of years ago with our quest today to understand the universe. As our journey of cosmic discovery continues, we remember its humble beginnings, the quiet nights, the patient observers, the dawning realizations. The stars that guided ancient farmers and sailors now guide spacecraft and still inspire us. The dawn of ancient astronomy was truly the first light of a grand adventure, an adventure that carries on every time we gaze in wonder at the night sky. In the stillness of a clear, ancient night, our ancestors gazed upward, seeking meaning in the patterns of the sky. They had watched the celestial dance for generations. Now, they yearned not just to observe the heavens, but to measure them, to mark the passage of time and the cardinal points written in the stars. Gentle curiosity was giving way to careful technique. In this soft darkness, a spark of understanding glowed. The cosmos could be mapped and counted, its rhythms woven into everyday life. And so began the quest to measure the heavens. The grass is damp with dew, and the air is cool and still. Picture a wise elder of an ancient village placing a stick upright in the ground under the morning sun. As the sun moves across the sky, the stick's shadow slowly shifts. By noon, the shadow shrinks to its shortest, pointing due north-south. By late afternoon, it stretches long in the opposite direction. Observing this daily pattern, our early sky watchers discovered a dependable rhythm. At one specific moment each day, the shadow aligns perfectly along a line. That is true noon, when the sun stands highest. With nothing more than a stick, a gnomon, as it would later be called, they began to read the sun's arc and find their bearings by its light. Day by day, season by season, they watched that noontime shadow. In summer, it grew short. In winter, long. By marking the tip of the shadow at noon throughout the year, they learned to recognize the solstices, the sun's highest path and its lowest. The changing shadow became a silent calendar etched in the dirt, telling them when the days would begin to shorten or lengthen again. What began as a simple observation of light and dark turned into a primitive sundial, an instrument that could divide the day and even foretell the turning of the seasons. From these simple beginnings, more refined instruments followed. In ancient Egypt, as midday shadows told of passing hours, artisans crafted small L-shaped sundials from wood and stone. These devices, with a short vertical rod casting a shadow on a marked horizontal scale, allowed people to gauge the time of day more precisely under the bright sun. Travelers and merchants could carry pocket-sized shadow clocks to plan their day's journey, using the sun itself as the clock's hand. By watching the moving shadow and noting its position on the scale, they could estimate the hour even far from home. But when night fell or clouds veiled the sun, different tools took over the task. One such tool was the water clock, a simple bowl or vessel with a tiny hole, allowing water to drip out at a steady rate. As the water level sank, markings inside the bowl revealed the passing hours. On a quiet night, you might hear the faint drip-drip of water keeping time, measuring the long hours till dawn. In temple courtyards, Egyptian and Mesopotamian priests measured the night watches by these dripping clepsydras, ensuring that even in darkness, time could be quantified. Through the slow emptying of water, they captured the essence of hours that the eye could not see. In the clear desert night of ancient Egypt, a different kind of timekeeper emerged among the temple astronomers. Two priests would climb to a flat rooftop and face north, each holding a merket, a carved wooden bar with a hanging plumb line. One priest aligned his merket with the North Star, establishing a true north-south line in the sky. The other priest sighted through a slotted stick, a bay, toward a chosen star. As the earth turned, the star drifted across the sky. When that star finally crossed the invisible meridian line, lining up perfectly with the plumb line of the merket fixed on north, the priests knew an hour of the night had passed. They would repeat this with a succession of stars, effectively dividing the night into equal parts, reading time by the stars themselves when the sun was gone. In this way, the Egyptians could tell time after sunset with remarkable consistency. Envision a clear Egyptian night on the rooftop of a temple in Thebes. A priest astronomer stands patiently, gazing northward. In his hand dangles a merket, its plumb line steady in the still air, and across from him, his apprentice holds another. One merket is carefully aligned with the North Star to fix the direction of true north. They wait in silence as the stars wheel overhead, the Milky Way a pale ribbon behind them. When a particular star approaches that north-south line in the sky, the priest signals to his apprentice. At the silent moment, the star crosses the meridian marked by the two merkets. The priest softly calls out the hour. Far below, in the darkness, an attendant notes the time and perhaps marks a water clock accordingly. Through these simple tools and careful eyes, they have divided the night into segments. Scenes like this played out regularly, allowing Egyptians to regulate rituals through all hours. The stars themselves became the ticking clock of their civilization. Over centuries, as civilizations blossomed, skywatchers refined their craft and invented intricate devices to model the heavens. Greek scholars, inheriting knowledge from Egypt and Babylon, devised instruments that brought the sky down into their hands. One such device was the armillary sphere, a framework of concentric rings representing the great circles of the sky. By swiveling these rings, for the celestial equator, the ecliptic of the zodiac, the horizon, and others, an astronomer could simulate the tilt of Earth and the paths of the sun and stars. With a sighting rod attached, they could point at a star or planet and read off its coordinates on the scaled rings. Using an armillary sphere, a learned Greek or Chinese astronomer could visualize the entire celestial dome in miniature, anticipating where a star would rise or a planet would cross the sky. This skeletal globe of rings was an Earth-centered model of the cosmos that one could hold and turn, an early attempt to chart the sky with mathematical precision and to understand the geometry of the heavens. Others in the Hellenistic world invented the astrolabe, part star map, part calculating tool, which became a cornerstone of ancient and medieval astronomy. Picture a flat bronze disc, its rim engraved with degree markings, and a smaller rotating disc, called the rete, cut with a filigree of pointers representing prominent stars. By setting a plate engraved for one's latitude onto the astrolabe, an astronomer created a tiny model of the local sky. On a clear evening, he could hold the astrolabe by a loop at its top so it hung vertically. Rotating the star map disc until a specific star, say red Antares in Scorpio, was aligned correctly, he could use a rotating bar, the alidad, to sight that star's height above the horizon. By measuring its altitude on the engraved scale and aligning the device with the horizon, he could determine the time of night or the time of year. Using the astrolabe's intricate markings, he might also predict when the sun would rise or set, find the current latitude, or solve a dozen other celestial riddles. With this small, elegant instrument, an astronomer could carry the whole sky's geometry in his palm. Now travel in your mind to a quiet Greek hillside around 100 BCE. Night has fallen, and a scholar carries a bronze astrolabe under the stars. He holds it up by its ring so it hangs straight, the etched star map on its face glinting in lamplight. Rotating the astrolabe's disks to line up the stars with the sky, he sights along the Alidade at a bright star low on the horizon. By measuring its height, he determines the time is a few hours past sunset. Next, he adjusts the instrument's parts to predict the sky at dawn, perhaps planning an early journey or an observation. With each movement of the astrolabe's parts, the scholar performs a miniature dance with the cosmos, a calculation of the heavens with a simple turn of metal. In that moment, as he peers at the tiny model of the sky in his hand, he transcends the darkness around him. He has harnessed the patterns above to answer practical questions below, bridging earth and sky with the art of his star-taker. Perhaps the most astonishing ancient instrument lay hidden for millennia beneath the sea. In the early 20th century, divers exploring a shipwreck off the Greek island of Antikythera retrieved corroded fragments of bronze gears. Once cleaned and studied, these fragments revealed an extraordinary mechanism from around 2,000 years ago, now known as the Antikythera mechanism. It was a kind of hand-cranked analog computer of the cosmos. Inside a shoebox-sized wooden case had been a complex assembly of interlocking gear wheels and dials. By turning a small crank, ancient astronomers could simulate the movements of the sun, moon, and possibly the 5 known planets through the zodiac. One dial likely showed the 365-day solar calendar, another the phases of the moon, and others the timing of eclipses, and perhaps the cycles of Venus and Mars. This device could predict eclipses years in advance, indicate the dates of future Olympic Games, and model lunar months, all with precisely cut bronze gears, no larger than a fingernail. In a time long before clocks or electronics, this mechanism was a marvel of human ingenuity. Its existence hints at knowledge and craftsmanship largely lost to time, a testament to how far the quest to measure the heavens had already advanced by the late Greek era. In the 3rd century BCE, one curious librarian in Egypt pushed the power of the simple gnomon to extraordinary lengths. Eratosthenes of Cyrene, working at the Great Library of Alexandria, had heard a fascinating report. In a southern town called Siena, modern Aswan, at noon on the summer solstice, the sun cast no shadow. It shone directly down a deep well. Intrigued, Eratosthenes set up an experiment. On the next summer solstice, he planted a tall stick, a gnomon, upright in Alexandria's sunlight, and carefully measured its shadow at noon. The stick did cast a shadow, making a small angle with its base. By measuring that shadow's length and knowing the distance between Alexandria and Syene, Eratosthenes calculated the circumference of the Earth itself. With simple geometry and a humble stick, he astonishingly estimated our planet's size within just a few % of the actual value. This was a triumph of human curiosity and reason, using the tools of the sky to measure the Earth underfoot. In one stroke, Eratosthenes proved not only that the Earth was round, but gave a remarkably close figure for how big it is. It stands as one of the great scientific feats of antiquity, all accomplished without modern instruments. These innovations in measuring the heavens were not confined to any one land. Far to the east in ancient China, astronomers also stood their measuring rods upright at noon, noting the shortest shadow at midwinter, to to mark the turning of the year. In imperial observatories, bronze circles and sighting tubes were crafted to observe the skies, and water clocks dripped steadily in palace courtyards to track the hours of night, just as in other lands. Across cultures, Egyptian, Babylonian, Greek, Chinese, and more, humanity gradually devised a shared language of measurement for the heavens. Different peoples under different skies found similar solutions, ways to catch time's passage in the swing of a shadow or the drip of water, ways to map the sky's dome with rings and rules. The impulse to understand the cosmos was universal. In time, the humble tools of the skywatcher became humanity's first scientific instruments, bridging earth and sky with curiosity and ingenuity. It's inspiring to consider that with nothing but shadows, dripping water, and careful eyes, our ancestors managed to tame time. They turned natural phenomena into rudimentary technology. In the arc of a sunbeam and the steady drip of water, they found rhythms that everyone could share. The seeds of science were being planted in those early experiments, a faith that the cosmos was orderly enough to be measured and predicted. These early astronomers and timekeepers were the first to domesticate the wild passage of time. Yet the quest to measure the heavens was not confined to handheld tools and small devices. Across the ancient world, people also turned stone, earth, and architecture into celestial instruments. They raised monuments, temples, tombs, stone circles, aligned with the sun, moon, and stars. These were giant observatories and calendars built into the landscape itself. By walking among these sites, one could read the calendar in the play of light and shadow, or find direction in the placement of stones. The very foundations of sacred spaces were woven with cosmic meaning, making the land a canvas for astronomy, where spiritual devotion and scientific observation met under open skies. On a broad plain in what is now England stands a circle of giant stones that have witnessed some 5,000 years of sunrises. Stonehenge, ancient, silent, and mysterious, is more than a ring of rocks. It is a monumental calendar and observatory crafted by Neolithic hands. Each year, on the summer solstice, the longest day, the dawn sun rises in perfect alignment with the heel stone at the circle's edge, sending a beam of sunlight through the heart of the monument. Crowds likely gathered in ancient times as they do today, watching the first rays of midsummer sun framed by Stonehenge's towering trilithons. On the shortest day of winter, at sunset, the sun's rays likewise align down the avenue through the stones, marking the year's turning point back toward light. These deliberate alignments show that Stonehenge's builders understood how to chart the sun's journey along the horizon with astonishing precision. Some researchers believe the arrangement of certain stones and pits at Stonehenge even tracks the moon's complex cycle, a 18.6-year lunar standstill pattern where the moon's rise and set extremes repeat. If true, this would mean the circle was not just a solar calendar, but a lunar one as well, a giant stone computer encoding heavenly rhythms. Within Stonehenge's timeless presence, one can still feel the echo of a Neolithic sky-watching culture, patiently marking the heavens' patterns with rock and earth. Imagine standing among those massive stones on a midsummer dawn, roughly 2500 BCE. A community has gathered in the pre-dawn hush, breath misting in the cool air, faces turned toward the northeast. The horizon grows slowly lighter. In the grey twilight, the outline of the distant heelstone is visible beyond the circle. Dew dampens the grass underfoot. There is an expectant silence, perhaps only the faint chirp of early birds and the soft rustle of a breeze among the stones. As the first brilliant edge of the sun breaks the horizon, A collective gasp or cheer ripples through the crowd. A golden beam streams in, aligning perfectly between two towering sarsen stones and illuminating the center of the circle. In that moment, night's chill is chased away by the sun's warmth. The people know the longest day has arrived. It must have felt as though the heavens themselves joined in celebration, as the king of day crowned their sacred space with light. Even long before Stonehenge, humans were marking the heavens in stone. In the western desert of Egypt, at a place called Nebra Playa, a humble circle of weathered rocks stands as perhaps the world's oldest known astronomical site. Over 7,000 years ago, well before the pyramids, cattle-herding people arranged stones here to line up with the summer solstice sunrise. Each year in late June, the dawn sun rising at Nebra Playa coincided with the arrival of life-giving monsoon rains in that once fertile region of the Sahara. For those ancient desert dwellers, the rising sun on that special morning was a promise of water and renewal. By embedding that moment in their stone circle, they could anticipate and celebrate the turning of the season. Nebra Playa's stones, small and simple compared to Stonehenge, nevertheless carry the same message. Our earliest astronomers were already tuning their lives to the motions of the sky. Far to the north in Ireland, another mysterious monument was built a millennium before Stonehenge. Newgrange, a great circular mound with a stone-lined passage leading to a central chamber, served as both tomb and cosmic clock. Every year on the winter solstice, the darkest day, a remarkable event occurs. At dawn, the rising sun's light floods through a carefully aligned opening above Newgrange's entrance. It travels down the long stone corridor and for about 17 minutes illuminates the inner chamber deep within the mound. In that brief glow, the spirits of the dead, entombed, there are symbolically touched by the reborn sun. Such an ingenious design shows how deeply Stone Age people understood and revered the cycle of the sun, crafting their sacred spaces to receive its light at the pivotal turning of the year. Now picture a scene in the cold midwinter dawn inside Newgrange's stone womb. It is the morning of the winter solstice in Neolithic Ireland, over 5,000 years ago. In the utter darkness of the tomb's central chamber, with the scent of earth and stone all around, people huddle in silence. Their breaths and the flames of torches flicker against stones carved with swirling spirals. All eyes are trained on the narrow entrance passageway. Outside, the pale sun creeps over the horizon. A narrow beam of sunlight suddenly pierces the darkness, snaking through a special opening, the roof box, above the doorway. Inch by inch, the beam extends down the tunnel, then bursts into the chamber, illuminating it with golden light. For a few wondrous minutes, the ancient carvings on the walls glow bright, and the faces of the gathered observers, which had been in darkness moments before, shine with awe. In that moment, the living and the dead are joined by the sun's triumph over darkness. The people know that even at the year's coldest, darkest time, the light will return. Newgrange's builders captured that promise in stone, marrying hope and astronomy in a brilliant display that still amazes us millennia later. On another continent, the ancient Egyptians likewise entwined their monumental architecture with celestial order. The Great Pyramid of Giza, built around 2500 BCE, is oriented almost perfectly to the cardinal directions: north, south, east, and west. This alignment, achieved with only rudimentary instruments, is accurate to a tiny fraction of a degree. Egyptian surveyors likely watched the stars, perhaps the circumpolar stars around the North Pole, or the shadow of a gnomon at true noon to orient the pyramid so precisely. Within the Great Pyramid, narrow shafts were engineered to angle out towards specific stars in the night sky. One southern shaft pointed toward the belt of Orion, a constellation the Egyptians associated with Osiris, their god of rebirth. A northern shaft aimed at what was then the North Star, Thuban, in the constellation Draco, around 2500 BCE. These star shafts may have been intended as pathways for the soul of the pharaoh entombed within, guiding his spirit to join the undying stars of the northern sky or the sacred Orion stars in the south. Thus, even in the design of a massive tomb, the Egyptians built a connection between the earthly and the cosmic, aligning their hopes of eternity with the stars above. Centuries later, Egyptians continued to align their holiest places with the sky. In the grand temple of Karnak at Luxor, dedicated to the sun god Amun-Ra, the entire structure was laid out along an axis that faces the sunrise of the winter solstice. On that December morning each year, the first light of dawn enters the temple's eastern gate and pours through its main corridor. Imagine standing at dawn in Karnak's great hypostyle hall on midwinter's day. The stone columns loom like a forest in the dim blue light before sunrise. Priests of Amun-Ra gather near the sanctuary deep inside. As the sun's disk peaks above the horizon, its rays shoot straight through the temple's gateway. A shaft of sunlight travels down the main aisle between the towering columns, cutting through motes of incense smoke in the air. In that heightened moment, the beam reaches the Holy of Holies, the sacred chamber at the temple's heart, and illuminates the statue of Amun. Gasps and chants echo through the hall as the deity is bathed in the newborn sunlight. It is as if the sun itself has entered the temple to pay homage. This annual solar alignment affirmed that the temple, and by extension the pharaoh's reign, was in harmony with the cosmos. The sun god had acknowledged his earthly dwelling, and the cycle of seasons was officially renewed. Another Egyptian marvel, the rock-cut temples of Abu Simbel in Nubia, demonstrates similar celestial precision. Carved into a cliff by Pharaoh Ramesses II in the 13th century BCE, the larger temple is oriented so that twice a year, around February 22nd and October 22nd, the rising sun's rays penetrate deep into its inner sanctuary. On those mornings, sunlight travels down the long entrance hall and illuminates the statues of the gods and of the deified Ramesses seated at the back wall, leaving only the figure of Ptah, a deity of darkness, in shadow. These dates are thought to correspond to Ramesses II's birthday and coronation day, making the solar event a celebration of his life and power. To stand inside the dim chamber at dawn on one of those days and see the faces of the statues gradually light up must have been a profoundly moving experience. It meant that the gods themselves, through the medium of the sun, were blessing the pharaoh. Abu Simbel's biannual solar spectacle is yet another example of the careful astronomical planning in sacred architecture, tying kingship and divinity to the rhythms of the sun. This practice of sacred alignment extended into Asia as well. At Angkor Wat in Cambodia, a vast temple complex built in the 12th century CE, the architects wove celestial cycles into its very design. The entire temple is oriented to the west, unusual for Hindu temples, and on the spring and autumn equinoxes, the sun sets directly over its central lotus tower when viewed from the entrance causeway. Additionally, the axes of Angkor Wat incorporate solstice alignments. At certain times of year, the sun rises or sets precisely along the temple's straight avenues, casting dramatic shadows through its doorways. These alignments were almost certainly deliberate, connecting the earthly capital of the Khmer Empire to the cosmic order. For the people of Angkor, aligning temple and sun, symbolized the harmony between their god-king and the universe. The temple itself became a cosmic diagram, integrating their calendar and cosmology into the very stones. Across the ocean in the Americas, the heavens were also a grand architectural theme. In the Maya city of Chichen Itza on the Yucatan Peninsula, circa 1000 CE, a pyramid called El Castillo dominates the site, and it is essentially a giant stone calendar. Each of its four faces has 91 steps, together with the top platform that totals 365 steps, corresponding to the days of the solar year. But even more spectacular is the play of light it creates on the equinox days. On the late afternoons of each spring and autumn equinox, as the sun descends, the northwest corner of the pyramid casts a series of triangular shadows on the northern staircase. These 7 dark triangles mimic the pattern of a serpent's body. They join with the carved serpent head at the base of the stairway, creating the illusion of a giant snake of shadow and light slithering down the pyramid. It appears as if Kukulkan, the feathered serpent god, is descending from the sky to the earth. This dramatic display happens exactly at the turn of the seasons, marking the beginning of spring or autumn, and likely drew crowds and ceremonies in ancient times. The people of Chichen Itza could watch this breathtaking performance knowing that their calendar was perfectly in sync with the cosmos. In the same city, another structure known as El Caracol, the snail, named for its spiral staircase, appears to have been an astronomical observatory. It's a round, tower-like building, and its windows and doorways are not randomly placed. They align with important celestial events. One example: certain openings correspond to the extreme northern and southern positions on the horizon, where Venus rises or sets. The Maya closely observed Venus, regarding it as a celestial twin of the sun and a portent for war and ritual timing. From El Caracol, priest astronomers could track Venus's appearances as the morning star and evening star through those slit windows, like looking through a gun sight. Other windows align with the equinox sunset and perhaps brightest stars of the season. The construction of El Caracol suggests the Maya built the very walls and apertures of the building to function as precise instruments, systematically watching the skies. In effect, the observatory's architecture allowed them to perform measurements and observations with the building itself, a testament to how advanced Mayan skywatching had become. Elsewhere in Mesoamerica, entire cities were planned with cosmic order in mind. The great metropolis of Teotihuacan in central Mexico, flourishing c. 100 CE, was laid out on a grid offset about 15.5 degrees from true north. Researchers have long debated the purpose of this tilt. Some suggest it aligns with the setting of the Pleiades star cluster, which was important in Mesoamerican timekeeping. Others propose it's oriented to the sun's position on a specific date, perhaps marking a zenith passage of the sun or a day related to their calendar. In effect, the very streets of Teotihuacan may form a giant cosmic diagram on the ground. Throughout Mexico and Central America, many other temples and pyramids display alignments to the rising or setting sun on equinoxes and solstices, from the Pyramid of the Sun at Teotihuacan to smaller shrine complexes. The widespread practice of marrying architecture with astronomy ensured that cities and sanctuaries mirrored the order of the heavens. High in the Andes Mountains, the Inca built their own sacred solar markers. At Machu Picchu in Peru, 15th century CE, a carved stone pillar known as the Intihuatana, the hitching post of the sun, was carefully positioned for cosmic effect. At noon, on the equinoxes, each spring and fall, the sun stands directly overhead at Machu Picchu's latitude. At that moment, the Intihuatana stone casts virtually no shadow at all. Legend says the Inca believed the sun was being tied to the stone to prevent it from wandering away. The Intihuatana thus served as a precise indicator of the equinox and a ceremonial focal point. Throughout the Inca city, other structures and windows align with solstice sunrises and sunsets as well. In the Temple of the Sun at Machu Picchu, for instance, a window is so oriented that the rising sun of the June solstice shines in and illuminates a specific sacred stone. These alignments reflect the Incas' deep astronomical awareness. They worshipped the sun as a deity, and by building their urban and ritual spaces in tune with solar events, they ensured that their human activities were synchronized with the will of the sun god. Even in North America's deserts, the skies guided sacred designs. In Chaco Canyon, New Mexico, USA, the ancestral Pueblo people constructed buildings and carved rock art that align with solar and lunar events. One famous example is the Sun Dagger site on Fajada Butte. Here, 3 upright stone slabs were positioned to cast thin slivers of sunlight onto a spiral petroglyph carved on the cliff face. At noon, on the summer solstice, a single narrow shaft of light pierces the heart of the spiral. At winter solstice, 2 shafts of light frame the spiral on either side. The cycles of the moon were recorded here too, during the moon's rare major standstill, an event that occurs every 18.6 years when the moon's rise and set reach their extreme northerly and southerly points. A shaft of moonlight falls in a similarly precise way on the spiral. Through these light and shadow markers, the people of Chaco Canyon could track not only the seasons, but also the longer rhythms of sun and moon. Even without a written calendar, their knowledge of the sky was literally etched into the living rock. It's humbling to stand at that site today, imagining the ancient observers watching a dagger of light or moonlight slide across the spiral, marking the passage of time with something as ephemeral as a sunbeam. Not all ancient sky alignments took the form of built structures either. On a vast, dry plain in Peru, the Nazca culture, c. 200 BCE, 600 CE, created enormous drawings by clearing dark stones to reveal the bright ground beneath. These Nazca lines depict giant animals, geometric shapes, and ruler straight lines that run for kilometers. Some researchers have wondered if certain lines or figures align with celestial events. For instance, if a particular line points toward the sun's setting on solstice, or a bright star's rising point. The evidence is still debated. Many lines seem more connected to sources of water or ceremonial pathways than precise astronomy. Yet the sheer scale and mystery of the Nazca geoglyphs, which are fully visible only from high above, show the lengths to which humans have gone to connect with cosmic or supernatural forces. Whether or not the Nazca builders intentionally aligned some drawings to the sky, the Nazca lines remind us that the dialogue between Earth and sky took many creative forms. They may have been giant star maps, ritual offerings to sky gods, or something in between. Whatever their purpose, they stand as an enigmatic chapter in ancient sky lore, prompting us to wonder about the unseen connections ancient people perceived between the ground they walked on and the heavens above. Under countless skies, these temples, tombs, and henges, aligned with the cosmos, served as calendars and observatories for their people. By reading the play of sunlight through a doorway, or the position of a shadow among stones, ancient societies could anticipate the seasons, knowing when to plant, when to harvest, when to hold feasts or rituals. These great structures in stone were, in a sense, giant instruments to capture time. But alongside these grand constructions, people also developed more abstract ways to track the passage of time itself. The careful study of the sun, moon, and stars gave rise to calendars, frameworks of days, months, and years that codified celestial rhythms for use in daily life. We step now into the minds of the ancient calendar makers, those who sought to tame time itself. Imagine an elder observing the sky year after year, noticing that the sun's warmth and the rains return in cycles. Perhaps they mark a notch on a stick or bone for each dawn or each full moon, gradually discerning a pattern. The need was pressing. Crops had to be planted at the right time, seasonal floods anticipated, and holy days set in harmony with the heavens. Out of careful observation grew the first calendars, living schedules shaped by the sun, the moon, and the stars, allowing society to plan and to celebrate in tune with cosmic events. Long before writing or cities, humans likely tracked time in simple ways. Archaeologists have found Ice Age bones and sticks etched with sequences of notches, possibly early calendars in the making. The famous Ishango bone from Central Africa, dating to about 20,000 years ago, bears groups of markings that some researchers think correspond to the phases of the moon. We can imagine a Paleolithic person carving a small notch for each day or each moonrise, creating a tangible record of the lunar month as it waxed and waned. Similarly, a 35,000-year-old baboon fibula, known as the Lubombo bone, found in Swaziland, has 29 notches, about the length of a lunar cycle, which might have been used to count days in a month. Though we cannot be certain these artifacts were true calendars, they hint that an awareness of the moon's roughly 29-day cycle dawned very early in human history. Even in the deep past, our ancestors may have recognized that the bright disk that grows and shrinks in the night sky keeps a steady count of days, a natural clock in the heavens. As civilization took root in Mesopotamia and elsewhere, calendars became more organized and systematic. The Sumerians and Babylonians, farming the fertile lands of the Tigris and Euphrates, observed that 12 lunar months, 12 cycles of the moon from new to full, made a year, but not an exact year. 12 moons totaled about 354 days, falling roughly 11 days short of the full solar year of approximately 365 days. At first, this discrepancy meant that over years the calendar would drift. Festivals that were meant for spring would start falling in winter, and so on. To keep the calendar in step with the seasons, Mesopotamian priests learned to occasionally insert a 13th month when needed. How did they decide? They watched the sky and the weather. If the stars and the timing of barley harvest suggested the calendar was off, a decree might be issued to add an extra month at the end of the year. By around 500 BCE, Babylonian astronomer priests had identified a useful pattern that became the basis for regular intercalation. In every 19-year period, 7 extra months needed to be added to keep lunar time aligned with solar time. This discovery, essentially the 19-year metonic cycle, later named after the Greek meton, who independently found the same pattern, allowed them to predict in advance which years would have that extra month. Using this cycle, the Babylonians could ensure that each spring planting and autumn harvest stayed on schedule under heaven's watch, with the months and stars once again matching the agricultural year. Let's travel to ancient Babylon on a clear night in the 5th century BCE. High above the mud brick city, a scholar priest ascends the steps of a tall ziggurat, a terraced temple tower, to reach the small observatory at its summit. Up here, above the glow of oil lamps and cooking fires, the full dome of stars reveals itself gloriously. The astronomer carries a damp clay tablet and a sharpened stylus of reed. He has been keeping a nightly log of planetary positions and unusual celestial events, part of the astronomical diaries that his temple has maintained for generations. Tonight, he watches for the first faint appearance of a particular star just before dawn, perhaps the star that signals the start of a new month. Hours pass as he observes, and makes occasional notes. In the cool pre-dawn darkness, there, a tiny spark of light appears low in the east. It is the star he awaited, making its heliacal rising, its first visible return after being hidden in the sun's glare. The priest presses his stylus into the clay, inscribing a small wedge-shaped mark along with the date and the star's name. In a soft voice, he might recite a short prayer or incantation acknowledging the god associated with that star. For even data-taking had a sacred element. This observation will be added to a growing archive of sky records. Such accumulated data helps the priesthood decide when to announce an extra month or whether an omen is at hand. For centuries, Babylonian astronomers compiled these nightly notes. Every midnight vigil atop the ziggurat, every careful entry on clay, quietly laid the groundwork for future discoveries. In the stillness of that rooftop, the movements of Jupiter, Venus, and the Moon become part of a grand pattern documented by human hands, a testament to patience and devotion to the sky. Beyond gathering data, Babylonian astronomers also sought meaning in the sky's patterns. Observing the heavens was not just about tracking time. It was also about seeking guidance and messages from the gods. In ancient times, astronomy and astrology were one and the same pursuit. The positions of planets and the occurrences of eclipses were thought to influence or portend events on Earth. Thus, along with numeric tables, Babylonian scholars compiled extensive collections of celestial omens. For example, they noted that if Jupiter, associated with a chief god like Marduk, shone especially bright in a certain part of the sky, the king might expect good fortune. A lunar eclipse might be recorded as foretelling the death of a ruler or a military defeat, unless rituals were performed to avert it. These interpretations were meticulously documented. If the moon eclipses on the 14th day in the constellation of the Bull, the king will die, the throne will not stand, and so on. Kings often had scholars watch the night on high alert around expected eclipse times. The belief was that the gods communicated through the motions of heavenly bodies, so one had to be literate in that cosmic language. Such was the birth of astrology. The Babylonians' omen catalogues became the foundation for later star divination in other cultures. The practice spread and evolved. The Greeks, during the Hellenistic period, absorbed Mesopotamian astrological concepts and developed horoscopes, personal astrological charts based on the exact positions of the sun, moon, and planets at an individual's birth. By the 1st century BCE, educated Greeks and Romans were casting horoscopes using the 12 signs of the zodiac, a Babylonian legacy. Similarly, in ancient China, astrologers at the imperial court monitored comets, guest stars, novae, supernovae, and planetary motions as omens reflecting the health of the empire. A sudden comet or nova in the sky could be taken as heaven's displeasure with an emperor, prompting rituals or even the sacrifice of the astrologers if they failed to predict it. While today we distinguish astronomy, the science of celestial objects, from astrology, the belief in their influence on human affairs, in antiquity the two were deeply intertwined. The same people tracking the stars' positions were also interpreting their significance. The night sky was viewed as a grand cosmic scroll on which the gods inscribed hints of the future, if one knew how to decode them. We can imagine an ancient Chinese court on the day of a solar eclipse. According to one legend, around 2000 BCE, two royal astronomers named Shi and He indulged in wine and neglected their duties. Suddenly, in midday, the sky began to darken. The sun was being devoured by something unseen. Panic spread among commoners, They banged drums and gongs to scare away the invisible dragon they believed was swallowing the sun. The emperor, however, was enraged. No one had warned him of this eclipse. She and he had failed in their task to predict the sky's omen. For this negligence, the story says, they were executed. True or not, the tale underscores how seriously ancient China regarded the mandate to keep the calendar and celestial omens in order. A mistimed calendar, or an unpredicted eclipse, wasn't merely an academic slip. It could upend the harmony between heaven and earth and invite disaster. The sovereign's fortune and the stability of the realm were seen as tied to the regularity of celestial phenomena. Thus, astronomy in China was a matter of state security. Court astronomers carefully observed solstices, measuring the sun's noon shadow with tall gnomons to pinpoint the exact day of midwinter, tracked the moon's course through lunar mansions, and noted every eclipse or comet. Their diligence was, in a sense, a job of cosmic risk management. If they kept the calendar aligned and interpreted heaven's signs correctly, the kingdom would remain in the gods' favour. Ancient India, too, cultivated an advanced understanding of celestial cycles. Vedic scholars divided the sky into 27 sections called nakshatras, based on the moon's daily progress against the background stars, a system not unlike the Chinese division of lunar mansions. Indian astronomers developed sophisticated lunisolar calendars, typically 12 lunar months in a year, with a 13th added as needed about every few years to keep in step with the seasons. Texts like the Vedanga Jyotisha, circa 1st millennium BCE, show that by late Vedic times, Indians were systematically calculating solstices, equinoxes, and intercalary months to maintain ritual calendars. Indian observers measured the sun's shadow with stone pillars, gnomons, to determine the precise day of the winter solstice, much as others did. If their lunar months began to drift too far beyond that solstice marker, or the expected season for monsoons and harvests, they knew it was time to insert a leap month. By the early centuries CE, Indian astronomers had also become adept at predicting eclipses and planetary conjunctions using arithmetic methods. They produced astronomical treatises, like the later Surya Siddhanta, with remarkably accurate constants for the lengths of the year and lunar month. All this shows that the quest to track the heavens was truly global. While Babylonians and Greeks were mapping planets in the west, Indian scholars were doing the same in the east. Their innovations in astronomy would later be transmitted westward via translations through the Islamic world. But in antiquity, they already formed a rich parallel tradition. From the Indus to the Euphrates, from the Nile to the Yellow River, ancient peoples, each in their own tongue and style, were learning to measure time by the sky. In the Mediterranean world, calendars underwent refinement as well. The Roman calendar, in early times, had been a messy affair based on lunar months with arbitrary insertions by politicians. It often fell out of sync with the seasons. By the 1st century BCE, spring festivals were drifting into what should have been summer. So Julius Caesar, upon consulting the Alexandrian astronomer Sosigenes, introduced a sweeping reform in 46 BCE. He abandoned the unpredictable lunar-based system and instituted a consistent solar calendar of 365 days, with an extra leap day every 4th year. This Julian calendar realigned the months with the solar year and provided a stability that previous Roman timekeeping lacked. With this change, the old link between month and moon phase was broken. The calendar became purely solar, much like the one the Egyptians had long used. The Julian calendar, with later minor tweaks by Pope Gregory XIII, became the basis of the calendar we still use today, a testament to how successful this ancient reform was. For the people of Rome and its empire, Caesar's reform meant that the dates of solstices and equinoxes would remain roughly constant from year to year. No longer would officials have to insert months at whim. Time had been nailed down by decree, following the lead of the heavens, rather than the convenience of politicians. On the other side of the world, the Maya civilization in Mesoamerica developed one of the most elaborate calendar systems known to antiquity. The Maya actually used several interlocking calendars. One was a 260-day sacred calendar, often called the Tzolkin, composed of 2 cycles, one of 13 numbers and one of 20-day names, cycling together like gears. Another was a 365-day solar calendar, the Harb, divided into 18 months of 20 days, plus a short 5-day period of ritual danger at the end of the year. These 2 calendars ran concurrently, and every 52 years their starting points coincided, a period the Maya called a calendar round. A 52-year calendar round was significant. It was roughly a lifetime, and when it completed, special ceremonies were held to mark the renewal of the cycle. But the Maya did not stop at that. They invented what's known as the long count, effectively a linear count of days from a mythological 0 date in the distant past, August 11th, 3114 BCE in our correlation. Using the long count, they could record dates centuries and millennia beyond the range of the 52-year cycle on stelae, carved stone monuments, in Maya cities. We find long count dates that correspond to times over 1,000 years in the past or future from when they were inscribed. The long count was broken into units. 20 days made a uinal, 18 uinals, 360 days, made a tun, almost a year. 20 tuns made a katun, 19.7 years, and 20 katuns made a baktun, 394 years. With such units, the Maya could, and did, refer to dates many baktuns away. For instance, they calculated and commemorated events that they believed occurred in mythic prehistory or would occur long after their civilization. It reflects a perspective of time on a grand cosmic scale, far beyond one human's experience. The Maya astronomer priests used their calendars for both practical and sacred purposes. They observed the sky meticulously and could predict eclipses and planetary appearances by recognizing repeating cycles. The Dresden Codex, a pre-Columbian Maya book, contains tables for predicting solar and lunar eclipses and tracking the complex cycle of Venus, which has significance in Maya lore as the morning and evening star. By following these tables, Maya priests could tell when Venus would reappear after inferior conjunction, when it's lost in the sun's glare, or when an eclipse was due. Such knowledge was intertwined with prophecy and decision-making. For example, wars were sometimes timed to the rise of Venus, a planet associated with warfare. Few ancient cultures had a sense of time as vast and intricate as the Maya. They saw themselves as players in a great cosmic cycle that went far beyond their era. To this day, people marvel that the Maya calculated their long count to span thousands of years. Famously, it completed a major cycle in December 2012, which stirred modern imaginations about what the Maya foresaw. For the Maya, every date was part of multiple overlapping cycles, all cycling in harmony. Time itself was something they observed, calculated, and revered as a divine element of the cosmos. Picture a Maya astronomer priest atop a pyramid in the city of Palenque about 1,200 years ago. The humid tropical night has fallen, but he is not idle. By the light of a torch, he consults a bark paper codex painted with glyphs and numbers. On one page is a series of date glyphs and symbols for Venus. It's the record of past Venus risings and a prediction for the next one. The priest murmurs calculations. He is determining when Venus will next appear as the morning star. Using the 584-day Venus cycle and aligning it with the 260-day ritual calendar, he counts the days since the last heliacal rising of Venus. Satisfied with his computation, he inscribes a forthcoming date on the codex, perhaps 5 months hence, when the brilliant star will once again gleam at dawn. That future morning will be propitious, maybe chosen for a royal announcement or a temple dedication. Now he turns to another section of the codex, an eclipse table. Scanning the rows of dots and glyphs, he checks if a solar eclipse is due soon. Seeing none immediate, he relaxes slightly. His ability to foresee such events lends great weight to his counsel. It means the gods have entrusted him with a portion of their secret knowledge. Above him, the jungle canopy is dark, and the sky is bursting with stars. The priest takes a moment to look up. The familiar constellations of his people wheel overhead, the Milky Way flowing like a great celestial river. He closes the folding codex and descends the pyramid steps, confident that his tracking of the heavens will keep his city's ritual calendar aligned with the cosmic order. In his records and predictions, he holds the threads of time that connect the Maya to the cycles of the sky. Through their calendars, ancient peoples found order in the passage of time. These schedules of days and months were more than convenience. They were a bridge between earth and sky, aligning human life with the cosmic clock. The ability to predict the flooding of a river or the return of summer by consulting the calendar gave a sense of control over nature's caprice. Priests and astronomers who kept this knowledge held esteemed roles as custodians of cosmic order, ensuring that planting started under the proper stars and that festivals honored the correct seasonal turning points. In every culture, calendar making blended the scientific with the sacred, turning observations of sun, moon, and stars into the very heartbeat of society. Having measured time and learned to predict the sky's cycles, ancient astronomers also sought to map the space of the heavens. They began to chart the stars themselves, identifying constellations, recording star positions, and creating the first celestial maps. By drawing pictures in the sky and plotting the wanderings of planets, they transformed the night's dome into a familiar landscape. We now turn to these star mappers as they trace outlines of meaning and myth in the glittering canvas of the night. A clear night sky is like a vast canvas of light. To ancient eyes unspoiled by urban glare, thousands of stars sparkled overhead in bewildering profusion. It was natural, perhaps inevitable, to find patterns in that glittering chaos, to connect the dots and weave stories among the stars. Around campfires on the steppe and in the courtyards of early cities, people pointed out shapes and gave them names. A hunter, a bear, a great bird, a set of twins. These imagined forms, constellations, were more than fanciful pictures. They became a practical map of the heavens, a mnemonic for remembering the stars, and a theatre for cultural myth. By naming and grouping the stars, ancient cultures made the sky more intimate. The distant pinpoints became characters in familiar stories, dependable markers that helped them navigate both space and time. Every culture drew its own figures in the stars, reflecting its environment and mythology. The ancient Greeks saw a multitude of heroes, gods, and creatures in the night sky. There was Orion, the mighty hunter, marching across the winter heavens with his shining belt of 3 stars. Perseus, holding the head of Medusa. Hercules, rising upside down. Pegasus, the winged horse. And a menagerie of animals from the lion, Leo, to the bull, Taurus, to the scorpion, Scorpius. They populated the celestial sphere with the characters of their legends. Far to the east, Chinese astronomers had an entirely different star lore. They partitioned the sky into regions like the Purple Forbidden Enclosure, near the North Celestial Pole, and the Heavenly Market. The 7 bright stars we know as the Big Dipper were part of what the Chinese called the Northern Bushel, or perhaps seen as a celestial bureaucrat's wagon. They wove their own myths. A great celestial dragon winding through the stars, or the azure dragon, white tiger, black tortoise, and vermilion bird guarding the 4 directions. In the southern skies, invisible to Greece or China, Polynesian navigators saw their guiding patterns, an immense southern cross, for instance, and they visualized a great fishhook of the demigod Maui in what others see as Scorpius's tail. Virtually every culture found meaning in the Pleiades, that small, misty cluster of stars, often likening them to a group of sisters or birds. To the Greeks, they were the 7 sisters pursued by Orion. To the Maya, a swarm of bees. To some Australian Aboriginal groups, a flock of cockatoos. And many saw a large animal in the bright stars around the North Pole. The Greeks and many Native American nations saw a great bear, Ursa Major, while to others it was a plough or a wagon. These shared tendencies hint at something universal. Humans everywhere peered at the same stars and often imagined similar things: heroes, animals, and mysteries projected onto the night. Among the Greek constellations, Orion the Hunter carries one of the most vivid legends. The Greeks told that Orion was a mighty hunter, boastful and beloved by the gods, who ultimately was slain by the sting of a giant scorpion sent by the Earth goddess. In the sky, they placed Orion and the scorpion at opposite ends. Orion rises in the winter sky, while Scorpius dominates the summer nights. The two are never seen together, as if the heavens keep the hunter and his slayer apart eternally. At Orion's heel gleams Sirius, the brightest star, as part of Canis Major, the great dog, representing Orion's faithful hound following at his heels. Night after night, the dog dutifully chases his master across the heavens. Such storytelling woven into the constellations made the sky a grand cosmic theatre for the Greeks. Each twinkling light wasn't just a burning star. It was part of a living tale played out eternally overhead, giving them a sense of drama and familiarity when they looked up at night. On the other side of the world, Polynesian wayfinders gazing at the same stars had their own interpretations. They often looked not only at star patterns, but at the dark spaces between. In Australian Aboriginal traditions, for example, a famous pattern is the emu in the sky. Instead of connecting stars, it is outlined by the dark dust clouds of the Milky Way. On autumn nights in Australia, this giant emu shape stretches across the sky. To the Aboriginal peoples, it signalled that real emus were laying eggs. Time to gather them. In stories, that celestial emu is often said to be a protective spirit or creator being. Aboriginal communities passed down an intricate star knowledge wholly through oral tradition. Songlines and tales that described not just constellations of stars, but constellations of dark nebulae, the paths of ancestor spirits, and seasonal cues encoded in the rising and setting of stars. Far from building stone observatories, these cultures carried their astronomy in memory and story. Yet it was no less effective. The night sky was their textbook and calendar. They knew, for instance, that when the distinctive shape of Orion's belt and sword, which they saw as the 3 kings or 3 brothers, appeared in the dawn sky, it was time to harvest certain foods. Or when Venus shone brightly in the west after sunset, certain fish would be spawning. This underscores that careful observation of the heavens is a universal human inheritance. It thrived not only in courts and temples, but also around campfires and under open skies wherever people lived. In Chinese star lore, the night sky told love stories as well as omens. One beloved tale is that of the cowherd and the weaver girl, represented by the stars Altair in the constellation Aquila and Vega in Lyra, which shine on opposite sides of the Milky Way's misty band. In legend, the weaver girl was a celestial maiden and skilled weaver of the clouds, who fell in love with a mortal cowherd. Angered by this misalliance, the celestial emperor, or the girl's father, depending on the version, separated them by a great river, the glowing river of stars we know as the Milky Way. Once each year, on the 7th night of the 7th lunar month, it's said that flocks of magpies form a bridge across the sky, allowing the two lovers to reunite for just that night. The Chinese festival of Qixi commemorates this story. Even today, it's sometimes called the Chinese Valentine's Day. People would look up hopefully at the sky on that evening. If it was clear and starry, it meant the magpies could meet and the lovers would find each other. If it rained, they said it was the tears of the weaver girl at missing her beloved. This tender story, played out in the heavens, gave a human emotional dimension to 2 points of light in the sky. The notion that stars Altair and Vega yearn for each other across the silvery river of the Milky Way is a poetic example of how deeply human feelings were interwoven with celestial observations. It's a reminder that across cultures, people not only navigated or calendared by the stars, but also poured their joys and sorrows into them, filling the silent night with the echoes of our most cherished stories. To truly map the heavens, ancient astronomers eventually began recording star positions and star groupings in written form. The first star charts and catalogues. One of the earliest known sky maps is not on paper or parchment, but cast in bronze. Discovered in modern times, the Nebra Sky Disk, c. 1600 BCE, is a bronze disk about 30 centimeters across, found in Germany. Inlaid on its green patinated surface are gold symbols: a big round circle, likely the sun or full moon, a crescent, the moon, and a scatter of 32 tiny gold dots representing stars. Among those stars, a tight cluster of 7 is easily recognizable as the Pleiades. There are also 2 long gold arcs along opposite edges of the disk, which span an angle of about 82 degrees. Interestingly, at the latitude of Nebra, 82 degrees is about the angle between where the sun rises at the summer solstice and where it rises at the winter solstice. A final golden arc at the bottom, added later, might represent a solar barge, an allusion to myth, or perhaps the Milky Way. This artifact is the oldest concrete depiction of the cosmos yet found. It seems to be a portable guide to the sky, showing key celestial objects and perhaps the sun's range on the horizon. One can imagine an ancient traveller or priest holding it up to align those arcs with the actual solstice sunrise and sunset points, or using it to teach others about the structure of the heavens. The Nebra Sky Disk beautifully illustrates that by the Bronze Age, people in Europe were not only observing the heavens, but symbolizing them in art and portable form, an attempt to capture the sky's patterns for reference and ceremony. The Egyptians, too, painted star maps on tomb ceilings and temple walls. These star ceilings depicted constellations and the divisions of the night. The tomb of Senenmut, architect to Queen Hatshepsut, c. 1460 BCE, contains one of the oldest known graphical star maps. On the plaster ceiling of his tomb chamber, yellow stars and figures stand out against a dark background. The Egyptians divided the night sky into 36 sections, known as decans, star groups that would rise in succession throughout the night, each decan marking roughly 10 days of the year, since 36 by 10 is 360 days, corresponding to their calendar, plus 5 extra days. Sen and Mutt's star map shows two halves: the northern sky, with constellations like the Big Dipper, which they saw as part of a bull's foreleg, and the southern sky, with the decanal stars and constellations like Orion, Egyptian Sahu, associated with Osiris, and Sirius, Egyptian Sopdet, associated with Isis. These star maps weren't just decorative, they had practical and religious significance. They guided priests in nighttime ceremonies and helped the deceased navigate the afterlife. The texts often implore the soul to join the imperishable stars that never set. To lie under a painted firmament with familiar constellations was to rest in a cosmos of order, even in death. Meanwhile, in the Hellenistic world, Greek scholars were compiling detailed star catalogues. Around 150 BCE, Hipparchus of Nicaea, often considered the greatest astronomer of antiquity, is said to have measured and listed the positions of about 850 stars with respect to the celestial poles and equator. He reportedly compared his star positions to those recorded by earlier Babylonian observers and noticed something intriguing. Certain stars' positions had shifted slightly over time. From this, Hipparchus deduced the phenomenon of precession, the slow wobble of Earth's axis that causes the celestial poles and equinox points to drift, a cycle of about 26,000 years. It was an astonishing insight, though at the time not widely appreciated. A few centuries later, in the 2nd century CE, Claudius Ptolemy in Alexandria assembled a star catalogue of over 1,000 stars as part of his great work, the Almagest. Ptolemy listed 48 classical constellations, essentially the Greek constellations that we still know in the northern sky, and gave the positions and brightness of stars within them. For example, he recorded the bright star Sirius in Canis Major, describing it as reddish and of the first magnitude. He placed Betelgeuse in Orion and Antares in Scorpio, and so on for all the prominent stars. Ptolemy's catalogue and constellation scheme became the standard reference for the next 1,500 years of Western and Middle Eastern astronomy. Though his positional accuracy was limited by the sighting instruments of the day, the idea of a mapped sky, with coordinates in the form of ecliptic longitude and latitude for each star, was firmly established. Humanity could now study a star map on papyrus or parchment and talk about the heavens in terms of degrees and arcs, not just mythic imagery. Mapping the stars was not only an intellectual triumph, it had profoundly practical uses, especially for navigation. Travelers and sailors learned to use the sky as their guide, long before magnetic compasses existed. The Phoenicians, great seafarers of the Mediterranean around 1000 BCE, navigated by the heavens. They famously relied on the steady position of the North Star, Polaris, to find north at night. Polaris is not exceptionally bright, but being near the north celestial pole, it remains fixed in the northern sky while other stars circle around it. Phoenician sailors crossing open waters would gauge their latitude by the height of Polaris above the horizon. The higher it appeared, the farther north they were. Many peoples discovered such techniques. In the southern hemisphere, where Polaris isn't visible, navigators used the Southern Cross and other star patterns to infer the south celestial pole. Knowing the cardinal directions from stars allowed them to stay on course when land vanished from sight. In the vast Pacific Ocean, Polynesian navigators achieved legendary feats of navigation using only their knowledge of the sky and sea. They memorized the rising and setting points of dozens of stars and constellations as seen from their home islands. At night, on a canoe in the middle of the ocean, a Polynesian wayfinder would have no instruments, but he carried in his mind a detailed star compass. He knew that, for example, the star Achernar rose due southeast and set due southwest, or that Hokulea, Arcturus, would pass directly overhead at the latitude of Hawaii. By watching what star was rising or setting at the horizon, he could maintain the canoe's direction. The navigator also understood how different stars took different paths across the sky, depending on the canoe's latitude, effectively allowing him to estimate when he drifted north or south of a target island. Through such knowledge, Polynesians travelled thousands of miles, discovering and settling nearly every habitable speck of land across the Pacific, centuries before Europeans ventured into open ocean. Their ability to read the stars, winds and waves impressed even the European explorers, who met them much later. It showed that a deep understanding of the stars, held in memory and tradition, could guide humans across the largest expanses of our planet. Mapping and measuring the sky eventually raised deeper questions. As star catalogues grew and planetary paths were plotted, some ancient thinkers began to wonder, what is the structure of the cosmos? How are these celestial lights arranged in space? While practical astronomy advanced, ancient cosmology, the theories of the universe's architecture, remained a tapestry of myth, philosophy, and emerging science. Ancient observers not only tracked the heavens, they pondered what the heavens actually were. Each culture envisioned the cosmos in its own way. The Egyptians saw the sky as the body of the goddess Nut arching over the earth. Her star-spangled form was drawn over tomb ceilings, with the sun depicted travelling inside her, swallowed at dusk, passing through her body at night, and reborn at dawn. The earth, Geb, lay beneath her, and the air, god Shu, held them apart. To the Mesopotamians, the world was a flat disk, afloat in a cosmic sea, covered by a hard sky dome like an inverted bowl. Above the dome were the waters of heaven. The stars were set or hung in this solid firmament. Beyond it was the realm of the high gods. Below the earth's disk lay the dark underworld. They imagined gates in the east and west, where the sun would enter and exit the solid sky each day. In ancient India, early Vedic texts spoke of the universe in poetic terms. The earth as a lotus flower blossoming on the cosmic ocean, or resting on the backs of elephants standing on a giant turtle. Later, Indian astronomy described a central Mount Meru and various heavenly layers. Yet Indian scholars also knew the earth was a sphere and calculated its size, merging mythic imagery with geometric insight. In China, the prevailing early model, the Gai-Tian theory, was that of a flat earth covered by a sky shaped like an umbrella or dome, with the stars as nails in it, though later Chinese astronomers considered that the heavens were infinite and the earth floating within, a more modern view. The Greeks, inheriting ideas from older cultures and adding reasoning of their own, developed several cosmic models. In classical Greece, 4th century BCE, philosophers like Plato and Aristotle taught a geocentric cosmos, a spherical, motionless earth at the center, surrounded by concentric crystalline spheres. Each sphere carried a celestial object, one for the moon, one for Mercury, Venus, the Sun, Mars, Jupiter, Saturn, the known planets, and finally, the sphere of fixed stars. These spheres rotated, producing the daily rising and setting of celestial bodies and the wandering of planets against the starry background. Aristotle's universe was finite, orderly, and hierarchical. Beyond the outermost starry sphere lay the prime mover, the divine source of motion. This elegant model endured for nearly 2,000 years in various forms. Yet even in antiquity, there were more radical ideas. The Pythagoreans, a sect of mystic philosophers, believed Earth was not the unmoving center. Philolaus, 5th century BCE, taught that Earth moved in a great orbit around a central fire, and that the sun, planets, and stars also circled this central fire. He imagined a counter-Earth as well, to complete a mystical 10 celestial bodies. Though not a heliocentric model per se, the central fire was not exactly the sun. It broke the notion of Earth's fixity. Later, in the 3rd century BCE, Aristarchus of Samos truly proposed a heliocentric model, the sun at the center and Earth orbiting it once a year, while rotating on its axis once a day. Aristarchus reached this bold idea by attempting to measure the distances of the sun and moon. By observing the moon during a half-moon phase and using geometry, he deduced the sun was much farther than the moon, in reality, about 400 times farther. Though his method underestimated the distances, he correctly intuited the sun was enormously large, far larger than Earth. It seemed reasonable to him that the smaller Earth might orbit the larger sun. Aristarchus's heliocentric theory was startling and gained little traction in his time. The geocentric view was far more intuitively supported by common sense and entrenched philosophy. His writings on the heliocentric model are lost. We know of them through references. And the idea lay mostly dormant until Copernicus revived it over 1,800 years later. The fact that one ancient thinker came so close to the truth is one of history's tantalizing what-ifs. Had Aristarchus's insight been widely believed, the story of astronomy might have leapt ahead centuries. But it was simply too revolutionary for the age. What all these cosmologies show is the earnest desire of ancient people to explain the cosmos on a grand scale. Even as they created ingenious instruments and calculations for what they could measure, they spun bold hypotheses about the unseen, what stars are, how far away they lie, what shape the cosmos takes. The true scale of the universe, the infinite space, the nature of stars, remained a profound mystery. But through myths and models, they placed themselves in a comprehensible cosmic order. Whether imagining the sky as a goddess's body, a crystalline sphere, or an enormous mechanism of wheels, they were bridging the gap between observing the heavens and understanding their place within it. Knowledge of the heavens did not remain isolated in one place. Throughout antiquity, ideas about astronomy flowed along trade routes and through scholars' travels. The Greeks, for example, learned much from Babylonian and Egyptian star watchers. Early Greek writings speak of Chaldean, Babylonian, astronomical lore, and Egyptian wisdom. Alexander the Great's conquests in the 4th century BCE carried Greek astronomical knowledge eastward as far as India, while bringing back new ideas westward. In the city of Alexandria, in Egypt, the Great Library became a meeting place of minds from different lands. Egyptian, Greek, Babylonian, Jewish, Persian, and later Roman scholars all exchanged ideas under its roof. This melting pot of celestial wisdom meant that techniques like the 19-year cycle for calendar intercalation, or instruments like the astrolabe, spread and cross-pollinated between cultures. As a result, by the late centuries BCE and early CE, one can find a kind of ancient global dialogue in astronomy. A Roman scholar like Ptolemy in Alexandria cited observations made in Babylon centuries before. An Indian text from the Gupta period references the Greek idea of epicycles for planets. Chinese records from the Han dynasty hint at knowledge of planets' synodic periods that align with West Asian findings. Even without modern communication, knowledge travelled, carried by traders, diplomats, wandering philosophers, and translated texts. This cross-pollination enriched each tradition's understanding of the sky. It built a cumulative legacy. Greek star catalogues built on Babylonian observations. Islamic astronomers later built on Greek and Indian calculations. And eventually European astronomy built on all of the above. But even in antiquity itself, the seeds of this worldwide sharing were planted. Human curiosity about the cosmos created a common ground that transcended language and empire. From the Nile to the Ganges, from the Aegean to the Yellow River, ancient astronomers were, in a sense, conversing, all part of a single human project to fathom the sky's mysteries. By the end of antiquity, humanity had learned to measure time and map the sky with remarkable skill. The sun, moon, and stars had become clocks and coordinates, built into monuments, calendars, and charts. Yet the ancient astronomers knew there was still much beyond their grasp. Distances unfathomable, wandering planets whose motions hinted at deeper laws, and fundamental mysteries about the nature of the cosmos itself. One ancient astronomer, Ptolemy, confessed that when he traced the movements of the stars, he no longer touched Earth with his feet, but stood beside Zeus himself. The night sky remained a source of profound questions and wonder. And so, our journey through these cosmic mysteries continues, moving onward from these early achievements to explore how later cultures and thinkers would build upon this foundation in the quest to understand the universe at an even deeper level. What other secrets did these early sky watchers uncover? What ancient insights lay hidden, only to be rediscovered centuries later? The story of humanity's relationship with the cosmos is far from over, and our exploration is set to continue in the chapters ahead, delving ever deeper into the enigmas of the stars. A new dawn was breaking in the study of the heavens. As the Renaissance spread its light across Europe, a few brave souls began to question the cosmic order that had endured for centuries. They did so quietly at first, under the same stars that had guided and confounded their ancestors. In cloistered university halls and lonely observatory towers, these thinkers dared to imagine a universe that worked not by magic or myth, but by discoverable laws. The transition would not be sudden or easy. It was a gradual turning, like the slow shift of the stars at midnight. But it had begun. The long journey from myth to understanding was now truly underway. In a modest cathedral city on the Baltic coast, a church canon named Nicholas Copernicus looked up at the night sky and contemplated an unorthodox idea. For years he pored over ancient astronomy texts and performed his own observations of the sun, moon, and planets. The more he calculated, the more the old Ptolemaic model with its tangle of epicycles bothered him. In the privacy of his study, Copernicus began to sketch a bold alternative. What if the sun, not the Earth, sat at the center of the known universe? In his mind's eye, he rearranged the cosmos. Earth became just another planet orbiting the sun, and the daily rising and setting of the heavens could be explained by Earth's own rotation. It was a daring thought, one that turned a millennium of accepted wisdom on its head. For decades, he refined this heliocentric theory, working cautiously to avoid ridicule or worse. Finally, in 1543, as an old man, he saw his life's work published. Legend tells that Copernicus, suffering from a stroke, awoke briefly on his deathbed to behold a copy of his newly printed book, smiling gently before passing away. Whether or not this tale is true, its symbolism is powerful. A quiet revolutionary gazing upon the new cosmic blueprint that would carry humanity forward. At first, Copernicus's idea made only a small ripple. His book was dense, written in Latin and dedicated to the Pope, and it presented the heliocentric model as a mathematical convenience rather than a proven physical reality. Many scholars admired its elegance, but hesitated to embrace its deeper implications. After all, if Earth moved around the sun, where was the evidence? One might expect to feel the motion, or to see the stars shift slightly over the seasons, an effect called parallax. Yet none was discernible with the naked eye. And there were philosophical and theological objections. In this scheme, humanity's home was no longer the center of creation. For a time, heliocentrism remained a speculative idea, discussed in academic circles, but not widely accepted. Yet the seed had been planted, and some minds were prepared to let it grow. A handful of astronomers across Europe quietly began testing Copernicus's theory, observing the skies to see if nature's behavior truly fit a sun-centered design. Not everyone who pondered the vast implications of this new cosmos was cautious. A fiery Italian philosopher named Giordano Bruno took Copernicus's model and pushed it to dizzying heights. Bruno proclaimed that if the sun was just one star among many, perhaps those other stars also had planets, even life, and that the universe was infinite, with no center at all. He envisioned a cosmos teeming with innumerable worlds, an idea far beyond what society was ready to accept. Bruno's passionate vision of an infinite universe was deemed heresy, and he paid the ultimate price. In the year 1600, he was burned at the stake in Rome. His fate was a stark warning of how dangerous it could be to challenge entrenched doctrine. Yet even as Bruno's voice was silenced, the ideas he championed continued to echo in scientific minds. The universe might indeed be far more vast and populous than previously imagined. While philosophical debates swirled, other astronomers focused on gathering concrete evidence. In Denmark, an eccentric nobleman named Tycho Brahe built a grand observatory on the island of Hven, determined to chart the heavens with unparalleled accuracy. Night after night in the late 1500s, Tycho and his assistants measured the positions of stars and planets using giant metal instruments and careful eyes, all without telescopes, which had not yet been invented. Tycho even named his observatory Uraniborg, the castle of the heavens, and equipped it with enormous scales and quadrants engraved with fine markings. In 1572, a brilliant new star flared into existence in the constellation Cassiopeia. Tycho recorded its brightness and position diligently. To his astonishment, he found that this nova stella showed no parallax shift against the background stars, meaning it was far beyond the moon, in the supposedly unchanging realm of the heavens. The old doctrine of an incorruptible celestial sphere had been shattered. A few years later, in 1577, Tycho observed a great comet streaking across the sky. By plotting the comet's path against the stars night after night, he realized it too traveled far above Earth's atmosphere, even passing through the region where the crystalline planetary spheres were thought to reside. The comet moved freely through space, as if those transparent cosmic shells did not exist at all. These observations boldly contradicted the tidy Aristotelian cosmos of nested spheres. Tycho Brahe, though he still believed Earth was at the center, had provided data that helped demolish the old framework and pave the way for a new one. Among those who found inspiration in Tycho's trove of measurements was a brilliant German mathematician named Johannes Kepler. Kepler had long been captivated by the harmony of the cosmos. As a young man, he even wondered if the spacing of the planets corresponded to nested geometric solids, an elegant but fanciful idea. Hired as Tycho's assistant not long before the Dane's sudden death, Kepler inherited something more valuable than gold: Tycho's detailed records of Mars's movements. Kepler set himself the daunting task of making sense of Mars's wandering path, using Copernicus's sun-centered model. For years, he labored, testing one hypothesis after another. The observations refused to fit any simple combination of circles. Frustrated but determined, Kepler finally tried a shape no astronomer had seriously considered before: the oval form of an ellipse. To his amazement, this slightly stretched circle, with the sun not at the center but offset at one focus, matched the data for Mars perfectly. It was a revelation. Mars, it turned out, did not move in a perfect circle at a constant speed, but in an ellipse, speeding up when it approached the Sun and slowing down when it travelled farther away. Before long, Kepler discovered that all the known planets followed the same rule. He formulated 3 laws of planetary motion that described these paths with astonishing accuracy. He marvelled at how the complex dance of the planets could be captured in relatively simple mathematical rules. To Kepler, it was as if he had glimpsed a bit of the clockwork behind creation, a blend of science and divine harmony that moved him deeply. Although the full implications were yet to be realized, Kepler's discoveries meant that the planets' wandering could now be understood not as capricious loops in the sky, but as orderly ellipses governed by the Sun's influence. Even as Kepler was unraveling the mathematical rhythm of the planets, another man in Italy was peering at the heavens in a way no one had before. In 1609, Galileo Galilei, a mathematics professor in Padua, heard rumours of a new invention from Holland, a spyglass that could magnify distant objects. Crafting his own improved version, Galileo pointed this first astronomical telescope skyward. One clear night, he aimed it at the moon, expecting perhaps a smooth pearl of light. Instead, he saw stark shadows and bright regions, mountains, craters, and valleys. The moon was not the perfect, unblemished orb philosophers had imagined, but a world with terrain not unlike Earth's. He turned his telescope on Jupiter and was startled to find 4 tiny moons circling the giant planet. 4 stars, lining up and changing position each night. Galileo watched them dance around Jupiter, proving that not everything in the heavens revolved around Earth after all. Galileo observed that Venus, too, showed phases like the moon, a cycle from crescent to full, which made sense only if Venus circled the Sun, catching sunlight from different angles as it orbited. He also realized that the pale band of the Milky Way was not a ghostly cloud in Earth's atmosphere, but countless distant stars too faint to see individually. Each discovery was thrilling. The universe was revealing itself to be far larger and more complex than anyone had imagined, and it certainly did not conform to the tidy perfection of ancient doctrine. Galileo's findings, published in lively letters and pamphlets, caused an uproar. Many scholars and clerics were deeply unsettled by what the telescope revealed. If the moon had mountains and pits, if Jupiter had its own moons, if Venus circled the Sun, what did that imply about humanity's exalted place at the centre of creation? Galileo argued fearlessly that the book of nature was written in the language of mathematics, and that our God-given senses, augmented by instruments, could reveal truths that might contradict literal readings of Scripture. This stance earned him dangerous enemies. Eventually, he was summoned before the Inquisition. Under threat of punishment, Galileo was compelled to recant heliocentrism publicly. It is said that after he capitulated in 1633, he muttered under his breath, "Eppur si muove," and yet it moves, asserting that Earth does indeed move around the Sun, no matter what he was forced to say. Whether or not those words were actually spoken, the sentiment was clear. By then, the evidence of Earth's motion was incontrovertible to those who had eyes to see. Galileo spent the remainder of his years under comfortable house arrest in a villa near Florence. Old, blind, but still full of ideas. He continued to write and think about the principles of motion and mechanics. His mind ranging freely through the cosmos he could no longer observe directly. Though officially silenced, his work spread across Europe, inspiring others to build better telescopes, to observe, and to question. The spark of scientific inquiry that he and Kepler had lit would not be extinguished. By the late 17th century, the outlines of a new cosmos were firmly established. The Sun stood at the center of the known planets, which moved in elliptical orbits. The Earth was one planet among several, and even moons circled other planets. The old crystal spheres were gone, shattered by comets and telescopes. Yet one great mystery remained. Why did the planets stay in their orbits? What invisible force kept them from flying off into space or spiraling into the Sun? The answer would come from an Englishman with an insight as revolutionary as Copernicus's. In the peaceful countryside of Lincolnshire, a young Isaac Newton sat beneath an apple tree in the mid-1660s, pondering the nature of motion and gravitation. He had been forced to leave Cambridge University temporarily due to a plague outbreak and found himself with ample time to think. As Newton watched an apple fall to the ground one day, he asked himself whether the same force that pulled the apple downward might extend all the way to the moon. Perhaps the moon was itself falling, perpetually, around Earth, held in orbit by the same influence that made apples drop. Over years of intense work, Newton developed his law of universal gravitation and the fundamental laws of motion. With exquisite simplicity, he showed that the very same gravitational force that causes an apple to fall from a tree guides the moon in its path around our world. In 1687, Newton published these findings in his great work, the Principia. The impact on astronomy, indeed on all of science, was monumental. The puzzle of the planets' motions was solved. They were held in their orbits by the Sun's gravity, following the precise mathematical laws Newton had formulated. For the first time, the mechanics of the heavens and the mechanics of Earth were unified under one theory. The distinction between the celestial and the terrestrial, so sharp in Aristotle's philosophy, melted away. The planets were not carried by angels or attached to crystal spheres. They were free bodies falling through space, their paths bent into curves by the pull of gravity, just as a cannonball follows a curved trajectory when tossed. The universe, it turned out, was one vast system governed by universal laws. The clockwork of the cosmos had been revealed, its gears and wheels described by equations that anyone could, in principle, understand. As the 1700s dawned, the night sky no longer held the same fearful mystery it once did. At least, not for the learned. Eclipses could be predicted years in advance. The once ominous comets were now recognized as periodic wanderers, bound by the sun's gravity. In 1705, Edmund Halley, using Newton's new principles, studied historical comet reports and realized that the bright comet he and others had seen in 1682 followed an orbit that would bring it back around in about 76 years. He boldly predicted the comet's return in 1758, long after he himself would be gone. Sure enough, when 1758 arrived, the comet appeared right on schedule, a triumphant confirmation of celestial mechanics. That very comet, which had so terrified kings and commoners in earlier ages, was now understood as a regular part of the solar system, as predictable as sunrise. The heavens had been, in large measure, demystified. Astronomy had shed its ancient role of astrology and magic. It had become a true science of observation, geometry, and physical law. Yet all this new knowledge did not diminish the wonder of the cosmos. If anything, it enhanced it. As each question was answered, new and deeper questions arose. Telescopes grew more powerful, revealing that the stars were not all at the same distance on a fixed sphere, but scattered across unimaginable gulfs of space. New planets were discovered in the outer dark, and strange blurry nebulae were glimpsed in the telescope's eyepiece. Galaxies and star clusters that hinted the universe's expanse might be far greater than even Copernicus or Galileo had dreamed. The more we learned, the more vast and majestic the universe appeared. From myth to science, we did not lose our reverence for the sky. We still name the planets after ancient gods. The constellations still carry the legends of heroes, hunters, and creatures spun by our ancestors. In a way, we have brought our stories with us on our journey to knowledge. But we have also learned to read the sky in a new way, as a cosmic story written in the language of light and gravity, open to any curious mind. The night remains, as it was to the ancients, a vast source of inspiration. But now we no longer feel so frightened or perplexed by its patterns. We know that Earth is not the center of all things, and that our sun is but one star among countless others. Rather than making us feel insignificant, this realization connects us to a grander tapestry of existence. We are part of the cosmos, made of the same stuff as the stars, and governed by the same laws. Imagine for a moment all the stargazers who came before us, from the first early humans who looked up in wonder, to the priest astronomers of Babylon marking celestial omens on clay tablets, from the Greek philosophers envisioning crystal spheres, to navigators in the age of sail steering by the stars, from the scholars of Baghdad and Samarkand preserving and enriching knowledge, to the daring innovators like Copernicus, Galileo, and Newton, who reinvented our understanding of the universe. Across thousands of years, across every culture, they all shared one basic impulse: to understand the lights in the sky. We today share that same spark of curiosity. When we gaze up at a clear night and feel the tug of the infinite, we are participating in a tradition as old as our species. Our journey through time and sky has shown us how far we have come. We began with fearful myths and wild imaginings. We end with confident knowledge of our planet's place in a vast, law-governed cosmos. And yet the final feeling is not one of conquest, but of communion. In uncovering the laws of the universe, we have not disenchanted the night sky. We have made it more profoundly beautiful. The cosmos above, once thought unknowable and divine, invites us now to explore and understand, while still inspiring our awe and humility. Now, under the quiet canopy of night, we can finally rest and reflect. The stars overhead, distant, silent, eternal, are the same that shone on the astronomers of ancient Mesopotamia, the philosophers of Greece and Alexandria, the sky watchers of China and India, the navigators of Polynesia, the scholars of the Islamic Golden Age, and the telescopes of the modern era. Generations have lived and died under this sky, each adding their wisdom to our collective celestial knowledge. As we conclude this long voyage through the chronicles of skywatching, we feel the presence of those generations alongside us. We are linked to them by our shared wonder and desire to know. The night is deep and calm. Constellations drift in their eternal courses. We have unraveled many secrets, yet the universe holds endless more, inviting future explorers to follow. There is comfort in that continuity, knowing that as we sleep, the stars will wheel onward, and tomorrow's curious minds will continue the quest. Our journey ends here, but the human story under the stars goes on and on. With a heart full of peace and a sky full of mysteries, we gently close the chapter of this cosmic voyage. May the eternal wonder of the stars always shine in the darkness above, guiding us, inspiring us, and reminding us that we are at home in the vastness of the universe.